My name is Vincent Kaufman. I'll be your chair for this session. We have a mixed session. We have some speakers that are online. We have some recordings, and there's a couple of people that are in person. I've heard word that Yamila might not be making it. She's not feeling well, so we'll see how that goes. Our first speaker will be Marie-Ève. She sent us a recording. She's hailing from Canada, so it's pretty early there. And yeah, she's going to be talking about using exoplanets teaching material in the classroom.
Hi, I am Marie-Ève. I am an astrophysicist and a science educator at the Trottier Institute for Research on Exoplanets. We also call it IREX at Université de Montréal in the province of Quebec in Canada. Our province is French-speaking, as you can maybe already tell from my accent. It's a very great honor for me to be with you here today as an invited speaker. I would have really liked to be in South Africa, but it was really not possible for me at this time of the year. So I decided to pre-record my presentation just to avoid any connection issue. But I will be here with you, so maybe we can chat a little bit after my presentation virtually or through the other means of communication. So I'm going to share my screen now to tell you a little bit more about a great project that was extremely fun to work on and to develop, and that I'm really proud to present to you today, especially because we've reached a great milestone this summer. So I'm going to tell you a little bit more about it. So the project is called Exoplanets in the Classroom, and it's also called Des exoplanètes à l'école in French. It's a bilingual educational suite for exploring exoplanet science. So this project was led in great part by our team at the Trottier Institute for Research on Exoplanets. And let me tell you just a little more about our great institute before to start talking to you more about exoplanets in the classroom. So we are a research institute located in Canada, in Quebec. We have a team of some 70 researchers who are not only world-renowned experts in exoplanet science. We like to detect exoplanets. We like to study exoplanets. We're also extremely strong in instrumentations. We were part of the team who developed, actually, we led the team who developed the Canadian instrument NIRIS on James Webb, among other projects. But we also have a strong wish to share our passion and engage discussion and exchange with the public in general in many different ways. So our program of education and public outreach is really vibrant here in Quebec, and we have a lot of experience working with kids, with teenagers, with adults in a variety of contexts. We led this project, Exoplanets in the Classroom, with many partners, notably the Canadian program Discover the Universe. Discover the Universe, I don't know if you know it already, but if you don't, I really invite you to explore it because it's a great program. It's a bilingual program, French and English, and at Discover the Universe, they are really experts in training educators in Canada and elsewhere. So we are really close to them in general. This is an organization we have a lot of connections with, and they were telling us how people were really interested about exoplanet science. Teachers wanted to have more resources. We all also realized that the kids were extremely passionate when we ourselves were going to classrooms, for example, and the teenagers were really interested. So we decided to create resources on exoplanets that Discover the Universe could use and promote in their trainings, in the material they are offering on their website, and also that we could use too. So you can see here a little bit more the people who were involved in this great project. I want to name astrophysicist Nathalie Ouellette, Frédéric Baron, and Heidi White, who are all part of the Trottier Institute for Research on Exoplanets at Université de Montréal, but also Observatoire du Mont Mégantic, which is a small-ish, medium-sized observatory that we have the chance to have here in Quebec. You can also see Julie Bolduc-Duval, who's the director of Discover the Universe. But what I want to emphasize is that one of the main features of our program, what it was led in very close collaboration with programs that are connected to teachers and teachers themselves. So I'm going to say a little bit more about that later. So we developed this program over a period of 3 years, actually 2 years for the main development in French that was funded by the provincial government of Quebec, especially to create resources for science teaching, science education in French. And then we spent another year translating these resources and implementing some of the programs. So of course, these were the years at the beginning that the pandemic was extremely affecting our life in many ways. So it had a major impact on what we decided on developing compared to what we had planned, namely that the web aspect took a much more big place. So what we ended up creating is really a web portal. So you go on our website and you can access a wealth of free resources that are all linked to the solar system, exoplanets, the search for life in the universe. Of course, we are passionate about exoplanets. Everybody at our institute really like to talk about all aspects of exoplanet science. But when we were in classrooms, we realized that we needed, of course, to expand a little bit. So we developed our resources to be able to talk about many different aspects of astronomy in general, of what an astronomer's career is, of who are astronomers who are working on this here in Canada. And we also put a lot of emphasis on interdisciplinary aspects. So I'm going to say a little more about that later. So for whom did we develop those resources? First, it was really for K-12 school staff, so teachers mainly. But then we realized that us ourselves could use it, but also a lot of other outreach initiatives who reach kids and teenagers can use this. Our main motivation, well, we had a few, but one of our main motivation was really to increase the number of available resources in French for French-speaking kids and teenagers. So in our province, most kids go to school in French. They speak French with their family. They speak French with their friends. So it was great for teachers to have resources in French to be able to talk about astronomy. And also we wanted to put forward those exciting fields of astrophysics that are extremely vibrant. You can probably see it through this symposium. This is a very active field of science, so we wanted to show the teachers and the students how exciting this field of research was. And one of our main also interest was really to put forward who are the people who are doing this science. So to provide a diversity of role models that the kids can maybe relate to, and also to increase the connection that the public can feel with the scientists. So we wanted to make ourselves really approachable and make a very accessible image of scientists. So we use the tagline resources for educator, by educator a couple of times. And this is really not a tagline for us. This is really what guided the project from the start. So more than 100 teachers in Quebec have been involved from the start up to the publication of the resources. They participated in brainstorming session. They tested the resources in their classrooms. They were consulted on many occasions to ensure that the resources were adapted to their realities and also their needs. And that's something that we had to do for the most part online because of the constraints brought by the pandemic. So we were not able to organize big workshops with teachers like we've planned. We were not able to go ourselves in classrooms at the beginning when we developed the resources. So all in all, for me, I think it was kind of a blessing in disguise because it brought many advantages. And one of them, the main advantage for me was that we were able to reach way more educators and also a greater variety of educators, or at least educators who work in a variety of contexts. So of course, if we organize workshops, it would have probably be in cities with teachers who are teaching in a particular setup in cities. We were still able to reach them through the web, but we were also able to reach other teachers. For example, teachers who teach in multi-level classrooms in small countryside schools. And we were able to bring in their comments and make sure that the resources we would develop were not only interesting for teachers who are, that they would be interesting for all teachers. Teachers who were at the beginning of their career or very far in their career, teachers who were really familiar and comfortable with science, others who were much less, teachers who were really interested in astronomy, and teachers who were maybe a bit they were not really interested at the beginning. And I think we succeeded in creating a small something for everyone. And it was really through those exchange that we were able to do with the teachers. So we experienced, of course, virtual meetings with teachers, virtual presentations, and I mean, presentations, it was more like discussions with classrooms. So we were able to see what the kids or the teenagers did and talk with them about the resources, and afterwards meet with their teachers, have their feedback. We used the virtual boards where they could show us what they did or pictures. We also tried social media. It was kind of good to recruit teachers, but it was maybe less optimal to have discussions with them. They were not participating as much as we would have liked. So this is something we tried, but didn't really much work. But anyways, we tried a lot of things. And then at the end of the project, it was great because we were able to go and talk in person to teachers and teachers conferences, and also to go in classrooms to see the resources used for ourselves. So that was great. And all in all, either virtually or in person, we were able to reach more than 1,000 elementary school students and secondary school students. So we were really able to see how the resources were used and fine-tune them so that they would be better for everybody. Now, we've learned a couple of things that I want to share with you during this process, namely about what are the needs or the different contexts in which the primary school teachers and secondary school teachers evolved. We realized that there were quite a lot of differences between the two. And actually, in the process, we brainstormed with primary school teachers, we brainstormed with secondary school teachers, we went on and built some draft resources, activities, and other supporting resources. Then we presented that to focus groups. And for the primary school teachers, they said, oh, that's great, continue, it's perfect, it's really what we wanted. But for the secondary schools, they were like, oh, wait, we have that and that and that constraint, and you need to to adjust. So just to be more specific, we realized, for example, that primary school teachers are able to take on activities that will take a few periods to complete because they are usually with their the same group all day, every day. While the secondary school teachers, they have the kids just for a small period and it comes back every now and then. So if it's not fitting in one period, it's usually not working because they have so much material to cover that they are much less interested about activities that take a long time. Primary school teachers, they teach everything, and the main focus of the program here in Quebec, but also in the rest of Canada, and I believe probably in many places around the world, the focus is really on language, French for us, and math. So if we can find connections or ways to do our activities that connect with French, mathematics, or also arts, it helps because for them it provides other ways to cover the topics they really need to focus on. While for secondary school teachers, they are specialists in science, so they usually don't really like interdisciplinary and multidisciplinary activities because that would involve working with teachers, but like there are schedules constraints and it was really complicated. So we had to maybe put those aspects of our activities in suggestions more than the core of the activities for the older students. The primary school teachers are maybe a little less confident in their capacities sometimes. Sometimes they are really confident, but sometimes less. And they really appreciate turnkey activities where everything is included and carefully explained. It can be longer description for the activities, and they really like that. Secondary school teachers, they like those descriptions, but usually they will take it and just make it their own, include it in something else that they've built, or like they will maybe more modify what we've done, we realize. And yeah, that I already said. Something that we realized is that there were some constant between all the teachers. All the teachers were extremely enthusiastic about featuring real scientists, local scientists, either through videos. We have a lot of videos in our resources, or through live presentations that we did during the development phase. They were really happy to have sources that they could trust, that were made by local experts. They were happy to participate to this program. So a lot of the participation they did was paid, but a lot of the participation was also volunteer, and it was not a problem to find volunteers for these smaller implications. They were really happy to be consulted. They were happy that we were listening to their advice and adjusting. So that was a very positive experience, and we built relationships with teachers here in Quebec that are lasting, and I'm sure that we will work with them again. A small aspect also is that all of our resources are free, accessible really easily online through a website that is not behind any kind of portal. There is no copyright of any sort, so they can use it, they can modify it, so that they really appreciate it. And something that we realized, and we made sure to respect this need, is that they are all very attached to their school program. So some of them extremely, some of them maybe a little less, but they really need to cover these things that are written in the program. So if we can make concrete connections to the program, which we did, it's much more easy for them to use those resources to convince their maybe direction that it's relevant, convince their colleagues, and feel confident that this is useful for their classrooms. So now I just want to show you a little bit how the resources look. So I'm going to try to go directly on the website because I think it's probably the best way. Okay, if I do that, and I go directly on the website, you can reach the website through the URL, the URL exoplanetsintheclassroom.ca. But when you end up here, it's a different URL. But what you'll see is a first explanation of what are exoplanets, a link to our institute so that they can know a little bit more about the IREX, Trotsky Institute for Research in Exoplanets. Then we have Google Slides presentation that they can use, a glossary, frequently asked questions, 2 teachers' guides, and I'll talk a little bit more about that later, that have activities that are developed for smaller kids and teenagers. Then biographies of some of our researchers. Then we have 2 series of videos. The first series is called Exobytes, and we have a couple of videos that presents various aspects of exoplanet science. I'm gonna touch up on this a little later. We built some tutorial for 2 software that are extremely useful for us. Not software, actually, web tool, Stellarium Web that you may know, and also Eyes on Exoplanet that I invite you to discover if you haven't. It's a NASA tool, and both we use them in some of our activities. So we built tutorial to help teachers and students to use them. We have flashcards. I'm going to show some of them to you. The second video series that is called Exoplanets and Us, that's meant to like connect the kids a little bit more to the people presenting. And a small encyclopedia, that's something that we still need to finish the translation, but it's available in French. Poster of some of your favorite exoplanets, and ways to contact us. So if I come back here, sorry. My PowerPoint. Okay, great. And we can talk a little bit more about some of the resources. So a small close-up on the resources. Well, the guides, the teacher's guides are really the core of the resources. We did one for younger students and one for older students, but we realized that the boundary is really not that clear-cut. So there are a lot of teachers working with secondary school students who like to use some of the primary school activity, and teachers who work with the smaller kids who will go and take some aspects of the older kids' activities. We also realized that the activities are like we were aiming for maybe 9 to 10 years old for the smaller for the younger kids, but then it can reach even younger kids than that. We were also aiming 12, 14 years old for the older kids, but we realized that a lot of our resources are really maybe more interesting even for older teenagers, so 16, 18, even university students. So we were happy to see that like there's a little something for everyone and it can be adapted. I really invite you to go and discover these activities for yourself, but I'm going to present one for elementary, from the elementary teacher's guide, and one from the secondary teacher's guide, just to let you know a little bit more what it's like. So in the primary school guide, there is an activity that I like a lot that is called Challenge, Explore the Sky and Exoplanets. In this activity, the students are challenged to make as many observations as possible: the moon and the sun, planets in the solar system, constellations, and even a bright star with an exoplanet. Along the way, they learn how different objects they can observe in the sky during the day or at night are related to exoplanets through small text, this text of the encyclopedia. It's observations that they can do in big cities like Montreal, so it's like the moon, the sun, bright planets. But if they cannot make observations for a reason or another, we also teach them a lot how to use Stellarium. So the teachers can use Stellarium to compensate or even just to bring back memories of the kids who made the observation. We do this activity every year in the winter in a more interactive way. So we send emails typically to teachers to invite them to do that observation or that observation that week. Usually lasts from December to end of January. So that's a very fun activity. And even the older kids can benefit from this activity, of course. The activity for the secondary school students that I'm presenting is related to James Webb. As I said, at IREX, we are extremely passionate about James Webb. A lot of our researchers use the telescope. We participated actively in the development of James Webb. René Doyon, our director, is also the PI for the NIRIS instrument and the fine guide sensor. I hope I'm saying that correctly, but anyways, we are really passionate about this telescope, and we want to talk about it with students. So we invite them to do a little bit what the astronomers do, choose an exoplanet, and explain in detail why they would like to observe it with James Webb. I say in detail, but it's a page, one side and the other side, so it's really adapted to maybe older teenagers. And then afterwards, so they do that in small teams, and afterwards they get in bigger groups and they do the time allocation committees. So they study the other groups' proposal, and they decide, or they comment on what were the strong point and maybe points to get better for every proposal. So it's really powerful for them to discover what is the work of an astronomer, what is a part of the work of an astronomer in a very concrete way, while learning more about exoplanets, telescopes. So we really like this activity. And to help them choose their exoplanets, we built these printable flashcards that are extremely appreciated also by the kids. There is another activity in the secondary school that use these flashcards. They need to figure out how they would classify exoplanets using those. We have, I think, 40 exoplanets, and we use the eyes on exoplanets, artistic rendition. So thanks to people who work on NASA's eyes on exoplanets, because we use the data of that to build the cards in French and English. It's also used by the primary school teachers for another fun activity where they imagine that they would travel to another exoplanet. So a very important aspect of our suite is the large number of supportive documentation we provide to teachers. So for every activity, for example, there are a couple of things that are suggested that the teachers can use to be able to make that activity, but these resources can also be used on their own. So for example, we have 5 slide decks on topics that can be used just to review content, or maybe to for the students themselves to discover topics. And all the image and there they have their where they come from, so that was also very appreciated. So that's something that that we really like developing, and that was really useful for teachers from what they told us. Oh, there's another set of flashcards that is more about planetary systems here. So this can be an extension of, maybe you already did that, the solar system in your neighborhood, where you do a scale version of the solar system, and then you can use the cards to explain a little bit more how the other systems are. So that's another set of cards that can be used on their own or with an activity. I said it before, one of the very appreciated feature of these resources are video series. There is one video series, Exobytes, that was made on its own first. It was a project we developed before, but then we realized it was fitting very well within the context of the project Exoplanets in the Classroom. So we decided to do biographies of all the scientists in the videos to accompany the videos, also quiz questions in case teachers want to use them just as a little thing, and also discussion prompts to accompany the Exobytes. And we also built another series, as I said, Exoplanets and Us. These videos are available in French with English subtitles. These are the biographies I was talking about. So everybody who's featured in the videos is also featured in the biography, and we try to make these really accessible to the public. So everybody's happy, students, teachers, the feedback they provide us was really positive. So we are extremely happy with that. And what we realize is that us, ourselves, astronomers, we use it a lot, either for fairs. We have a day camp at our university that is specializing in astronomy. So we use our activities. Career Day, that activity where the teenagers would imagine which planet they would observe with James Webb. We usually do it on career days. Animation we do in classrooms and libraries and other places. So yes, for us two astronomers and our grad students or researchers, it's also very helpful. So what's next? So we need to finalize the English documents. As you saw, it's not all finished. We will do a very official back to school launch in the fall. That there will be also seminars for teachers. You can check the website for that. There will be the Explore the Sky Challenge again this winter. And maybe we will try a program training ambassadors because we realized through another project that I'm going to touch upon in just a minute that the graduate students are extraordinary ambassadors for these activities. And that's the little thing I want to mention at the end. It's totally unrelated, but in Montreal, we had our total solar eclipse on April 8th. We did a lot for that, bought classes, made events, trained ambassadors. We were also part of a group, Eclipse Quebec. We made a website. So if you want to hear more about that, please contact us. And my very last thing is that I want to invite you all in July of next year to come in Montreal for exoclimbs. That would be extraordinary. So on that, I want to thank you very much for your attention. I was really happy to have this chance to talk to you about exoplanets in the classroom today. Please don't hesitate to contact me. Bye-bye.
Thank you, Maria. That was lovely. That's it's awesome work. We have a couple of minutes for questions since the schedule opened up a little bit. I don't know if there's any questions online or if there are any questions in the room. There's a microphone in the back, please. Yep.
Hi, this is really great, amazing work. This is Rafael Luque from the University of Chicago. I was wondering if you have any plans or you are already in contact with some people to put these materials in different languages, or are you looking for collaborators to do so? Because I'm certainly that we would be happy to contribute to the Spanish translation. So yes, I was wondering if this is a work that is already ongoing or you are looking for partners. Yeah.
Hi. Hi, thanks for a very good question. I don't know if you can hear me. I can see you actually because of the camera in the room. This is a very, very good idea. We've already, we created the resources in French thanks to the government of Quebec who wanted to get more resources in French available. And then due to the big demand, we decided to translate it in English. And also because Canada is mostly French and English, but we are more than open to see these resources translated in more languages. Spanish would be very, very great because it would allow us to reach many countries around the world. Especially I'm thinking about many collaborators that Discover the Universe have in South America, for example. So just feel free to contact me if you want to make this possible. I would be very, very happy to work on this.
Thanks. Yeah, that sounds like a great idea. Are there any further questions? I'm going to look here online. No questions online. If not, then I would propose that we proceed with the program. So the next speaker will be Thomas Fauché. He's here in the room and he will talk to us about the Cuisine's model intercomparison project, specifically for exoplanets. Thank you, Maria.
Thanks.
Thank you, Vincent. Hi, everyone. I'm Thomas Fauché from NASA Goddard in American University. Hopefully my slide will arrive soon.
There we go.
Perfect, thank you. And yeah, today, so in my presentation, I'm going to update you on the last results on the Cuisine project, which is a network to develop and host intercomparison of model for the exoplanet community. And specifically in that presentation, I'm going to focus on the projects that are connected to James Webb. And so as we have seen, in this conference, we have not discovered like over 5,500 exoplanets and still counting. And we are really have been astonished by the huge diversity of worlds that we have detected. And that world diversity is only matched by the amazing variety of models that we have to study them. And so to study those exoplanets, basically we use those models for two big things. Either to predict the data, let's try to understand how different exoplanets may have a certain type of atmosphere and climate, and how can we use those this kind of understanding to predict what the observation could be for James Webb, for instance, and therefore asking for a certain amount of observing time to detect a given features. The other aspect of using those models is to do the data interpretation. Once we get a spectrum, how can we extract information from it in order to better understand what's going on in this exoplanet? Okay, and so the problem is that we have so many models that when we have different models in the same category developed by different groups around the world, if they make different predictions, how do we know which model is closer to the truth? And well, the problem is that we are in such a limited data environment that we cannot really know that because, we don't have a ground truth. When we do Earth science, we have different models. We can still compare to the huge amount of data and to some extent for solar system objects as well. But for exoplanet, it's very difficult. So we cannot do that, but at least if we compare models together, we can quantify differences between their prediction. And that also lead to mitigate the model dependencies because it's really something we want to avoid. We don't want to have some conclusions that are dependent of the use of a given model. And comparing models together really help to track down bugs really that we can have in a code that we didn't see before comparing and benchmarking with another code. And at the end, again, that helps to bracket the prediction between this variety of model, between minimum and max value, and having mean standard deviation across the prediction. And also something is that important is that helps to highlight as well area of necessary development when we have maybe one code in the intercomparison project that is a bit behind in terms of parameterization and processes that are taken into account that really also sort of help and push the model to keep developing the code. And in the end, the ultimate goal is to provide to the observer a more robust and a less model-dependent prediction and data interpretation. And this is very fundamental. We have to do that as a community because we cannot really afford to have prediction that depend of a given model, specifically when after we are moving towards searching for biosignature, which is a very sensitive subject, and we have to be very careful with model dependencies. And so the Earth science communities have done model intercomparison for decades and decades, and have been proven extremely useful. And here we have a figure from the CEMIP, the Global Climate Model Intercomparison Project that really helps to understand the current climate on Earth and its future evolution. And we can see on this plot here that these different GCM all predict an increase of the global temperature on Earth. But the amplitude varies depending of the model. And so right now we have in CEMIP 7 that is started, but this is really CEMIP 6. And the first version is back to 1995. And again, that's been very, very important to quantify the different prediction between those models that are extremely complex and rely on some parameterization. And therefore, we need to do this comparison. And that's what we try to leverage here with the Cuisine project. And so Cuisine is an acronym that was really suitable for that because we can really have a lot of flavor of exoplanet, like a sort of menu. And so it all started because the very first intercomparison in this project was the Thai intercomparison because it started at a Thai restaurant when exoplanet GCM modelers, they gathered together and they're like, okay, GCM are very complex models. We need to benchmark them. And so I'm the founder of the Cuisine project. I'm the co-lead now with Denis Sergeev, University of Exeter. And I'm going to present after. We have many projects within that. And all of us are the cuisine chefs. And so let's look at the 5 courses of cuisine, like the big principle behind this project. First, when we want to do an intercomparison, we need to define in advance what research question the Exoplanet Model Intercomparison Project, ExoMIP, is intended to address. We don't want just to do intercomparison for the sake of it. It's quite an exhaustive, and difficult effort. So we need to have a defined science question for that. And then once we have that, we want to create an experimental design that maximizes the community participation and advertise it widely, which means that every intercomparison we do in that project, we first published a protocol paper that really explains the intercomparison and all the inputs, outputs we are expecting. And we do not include results in that paper. And the idea is really to have this protocol completely separated so people can then see it online and then join us, ask to join the intercomparison along the way. Because if you publish everything all together, people are, oh, I wish I would have been participating to that project, but now it's gone. Doing that in a 2-step process really helps for the participation. And therefore, then we also try to plan a timeline that allows all the ExoMIP members to participate fully. We are really aware that doing intercomparison, it takes a lot of time. So we are really mindful of everybody's time and really try to have a timeline that suits everyone. Also, it's very important to generate data products from the model output for direct comparison to observation. That's also the thing with cuisine. Even when we compare a lot of atmospheric models together, we always try to connect all the differences between those atmospheric models impact the predicted observation or even the interpretation. And finally, that is really dependent of creating a good data management plan that meets the current needs and that also grow and adapt as cuisine evolve, because of course, we try to follow the new observation that we have of exoplanets. And so a good data management plan is fundamental here. And so in terms of missions, well, first mission is really helping the community to understand how their model perform with respect to each other. And therefore, building new collaboration as well. When we do intercomparison, we really connect to different groups across the world is very important. And then we really increase the collaboration and sharing of the tools as a community. And what we also do is we provide permanent benchmark for exoplanet models. When we have done the comparison between the model, we have published the results in papers. We have all our results permanently available. So even if like 5, 10, 15 years down the road, someone else in a different group want to compare their model to this intercomparison, they can do it at any point of time. And as mentioned earlier, all that will hopefully mitigate model dependencies and providing across model average and standard deviation for both the data prediction and interpretation. And also, it's very important for us. We also involve a lot and train the early career researcher in exoplanet models and comparison procedures. When I started like the TIE project years ago, I started without having any experience on GCMs, and I really learned a lot through comparing them. And it's actually a great thing to quickly learn a model. And so here is where we stand right now as the cuisine project with all those fun logos and acronyms related to cuisine and food. They are really for different categories of exoplanet and models. If we start on the very top here, we have MOCA led by Nicolas Hiro. It's about hot and ultra hot Jupiters with GCM. On the right after we have Philae by Russell Detrick. It's about energy balance model, EBMs. Jacob Akmisra does GCM, any kind of model, actually, a climate model for a sparse sampling approach. Amber Young starting the risotto intercomparison for retrievals. Geronimo Villanueva here in the room for a Malbec, it's all the forward relative transfer model. Sonny Herman for Pi is the 1D photochemical models, followed by Kodakra, which are the 1D climate model. Duncan Christie, you lead Camembert, which is the GCM for mini Neptunes, K218b, GG1214b. Tai was myself for TRAPPIST-1E and GCM, and finally Crème for Kostas Sigaridis, who had the idea to say, let's use those exoplanet GCMs and see if we are able to reproduce Earth correctly, because now we have some ground truth, and maybe those exoplanet models have diverged a lot from their parent model on Earth and may not be as good as reproducing Earth. And so I'm just going to go there very quickly, an overview of the one that are more involved with James Webb. But yeah, before that, in terms of resources, we have a website that you can access through the QR code. It's on site the Next. So we are a Next Science Working Group. It's a NASA Nexus for Exoplanet Studies. And every script that we have are hosted on GitHub, because we don't only want to make all those data there available and use this huge netcdf file. No, we make everything accessible, which means that we provide all the scripts to extract the data, to compare them, to plot everything. It's really the accessibility which is fundamental here, so people can easily use our model outputs and compare with their own code. And all the data here are hosted on the NASA EMAC here on Seacon, which is a web interface. And we have really gigabytes or terabytes of data there available, again, for long-term archiving. And so, as I mentioned earlier, the very first project was TIE, and the motivation was to try to use different GCMs to simulate the most habitable exoplanet we know so far, or at least we knew, was TRAPPIST-1e. And we had 4 GCM, where the first one was a Rocky 3D from NASA GIS. We had ExoCam developed by Eric Wolf based on the NCAR model CAM. We had the LMD generic model in Paris and the METOFIS unified models. And what was very interesting is, like, even if we have exactly the same set of inputs, for example, here we try to simulate a modern Earth-like atmosphere with water at the surface, we ended up with some different planets, and specifically the clouds. The clouds are heavily parameterized within GCM, and depending on which GCM we have used, we have ended up with more or less clouds, thicker, thinner, higher, or lower. And the clouds have a massive impact on transmission spectra that we can simulate. And so what we did, we took each GCM atmosphere and the terminator, we simulate JWST transmission spectra, and we ended up with slightly different spectra, because the clouds, the latitude of the cloud deck is going to define where your continuum level is, and that's therefore going to shift your spectrum up or down. And so at the end here, this quick table, what we started to do is, like, we have those 4 different atmospheres. The first, band 1 and band 2, are dry, no water at the surface, with a modern Earth atmosphere and 1 bar CO2. And then we have the equivalent with water at the surface, HAB1 and HAB2. And we have those 4 GCM I mentioned here. And the numbers that you see there are the predicted 5 sigma detection, the number of transits we will need with Webb to reach a 5 sigma detection of CO2. And quickly here, when we look at the cases that are habitable with water and clouds, we have actually a 50% difference in the number of transits that will be needed if we use one GCM or another. So 50% is a lot when you then want to submit some JWST proposal time. If you have used one model or another, you can have a large differences of prediction. And then Duncan Christie here wanted to extrapolate that to different kind of planets, and specifically the mini Neptunes, JJ1240b and K218b, that are a great target for Webb. And with those GCM, it's also very quite complicated. It takes a lot of time to run those GCMs. And very briefly, as preliminary results here, Duncan made this video there when we are looking at only a subset of those GCM, and we are looking at the temperature maps at 1 millibar, and you can see that they look quite different right now between those 4 GCM, and we are still trying to understand the source of differences. But you can see like that, if then you try to simulate a phase curve, you're really going to get something different, and therefore impacting also your interpretation of the data we got for Webb. Then we have Malbec. Geronimo here is a chef, he's in a room that's really doing the intercomparison of radiative transfer tool. We have a lot of models here in this list. This project started a few years ago. And last year, Geronimo published the protocol paper that showcases just one simple case here of the subneptune GJ1214b with a lot of different radiative transfer model. And that looks like what Nathalie Batala yesterday presented for different planets. And similarly, we have at first had a lot of issues to get those spectra as close as we're seeing right now, because different assumption into the radius, what with the Earth radius or Sun radius, star radius, all the constant, but also all the atmosphere was discretized. How many layers do you need? All that was strongly impacted the results. At the end here, we have a relatively good agreement. We still have differences that are intrinsic due to different line lists. Are they using, correlated K, line by line, cross section? Do they include collision absorption or not? What kind of broadening? The use of isotopes for water or not? All those parameters are still impacted a bit the results. And now we have Estelle Janin here that is leading the results paper focused on all the transit observation for different kind of planet. And Eleonora Alley does that for the direct imaging side, so more connected to HWO. And then the last one that started this year is led by Amber Young at Goddard. It's Risotto. So it's really looking into the retrieval and connected to JWST, of course, but also HWO and anything in between. Because even if we have our climate model that perfectly agree, if we have a radiative transfer forward that perfectly agree, which could still have differences due to the retrieval code, it's very important to benchmark. And so, yeah, I'm going to finish on this slide, reminding you again the resource here that we have on the Cuisine website. All those intercomparisons are open to everyone. So if you have a code and you want to participate, please reach out to me on the Slack of the IAU. I will be really happy to welcome you there. And also if you have a different category of model we don't have yet and you want to propose, this would be great as well. Knowing that this year we are going to have likely a new one that's going to be the interior models connected to atmosphere. It's a big category of models that we need to benchmark as well. Every year we have a workshop we call Buffet. That's going to be in October, mid-October. So Sam, if you want to join, please let me know. Thank you very much.
Thank you very much, Thomas. As you can see, the schedule cleared up a little bit since Emilio was ill, so we have some time for questions for Thomas. Question here at the front.
This is more of a comment than a question.
Mm-hmm.
In astrophysics, systematic errors usually dominate over random errors.
Yeah.
And many times I see analyses of comparing models to observations, you minimize the errors and you come up with an answer. And if the physics is missing, the answer is irrelevant.
Mm-hmm.
The Earth's climate is nonlinear, very
Mm-hmm.
nonlinear,
Mm-hmm.
which is why predictions don't go very well. And comparing the Earth to Venus, two planets that are, you would think, are very similar, have totally different atmospheres.
Mm-hmm.
So my comment is, it's really important to get the physics right.
Yeah, absolutely. No, it's a great point. It's a great point. And when we do those model intercomparison, because we don't really know where the ground truth is, we don't necessarily improve our accuracy, but what we improve is the robustness, which means that we get a greater agreement among the model. But that we always like to say, therefore, when we do that, we either are all right together or all wrong together. But at least we are together because then we avoid the model dependencies. And yeah, so it's really achieving a high robustness rather than a high accuracy.
Thank you. Thomas, I had a question as well, if there's no
Mm-hmm.
question. What would be, if you could pick one more intercomparison that you think would benefit exoplanet science a lot, what would what would you like to start?
Okay, yeah, great one. Yeah. Well, I mean, the interior model that are about to start, it's really something I wanted to see. But I think escape as well. The escape processes will be really interesting because they can really also fundamental, right? To see if an atmosphere can survive in different kind of environment. And they are also very complex models with a lot of parameterization, and we definitely need to look into the escape processes as well.
Right.
Thank you.
And what about stellar models?
Yes, absolutely. Yeah, I mean, that's a good point. That's sort of a lot of our inputs, right, in all those models here. Why not? I mean, at some point, it's something we may want to look at. I know also that we have a colleague at Goddard would be really interested to include intercomparison of lab data, because they also provide a lot of input for us. And it's very important to start at the beginning also to actually agree on our inputs. And yeah, everything can be interesting at this point, yeah.
That would be quite shocking, I guess, if we start finding out, it's like, actually, guys, like if someone else measured the same same parameters, they're very different. Then
yeah,
I think that would be troublesome.
Exactly.
Thanks. Do we have any questions online? Not for now. Okay. If there are any other questions for Marie-Ève, she's still online, perhaps as well. I'd like to open it up for her too. Yeah. Okay.
Yeah, we got a question from Mariam. Could you give us the reference paper of the simulated transmission spectra of GG1214b? Which paper that was?
GG1214b?
Oh, yes.
Can you say again the question?
Which paper that you got the simulated transmission spectra of GG1214b?
Or it will be? Yeah. But yeah.
Which paper that one she?
Villanueva et al. 2023. Yeah. And so that was the protocol paper of the Malbec intercomparisons. And even if we try to separate the result from the protocol, we at least want to showcase one case in each protocol. And that one was one of the best because it's a really a good target for web.
Thank you.
Thank you.
Awesome.
Yeah, if you want the old resources also in the Cuisine website, again, if you come back on the QR code here, for each of an intercomparison, you will find all the resources, including the papers. So yeah, everything will be there. We have a special issue into the Planetary Science Journal that really hosts all the papers related to the Cuisine project.
Yeah, so if you guys have any questions and further comments, like we're here at the conference, so ask Thomas, or if you're specifically interested in Malbec, Geronimo's in the back.
And I have stickers as well.
There we go. So I would propose that we move on. Our next speaker will be Emma. She's online. I think we're gonna thank Thomas for his time and his questions. Emma, if you can try and share your screen.
Yes.
We can hear you in the room.
Okay. I'm trying to share. Okay, can you see my screen?
Yep, they're used to. Okay, they're bringing it up.
Okay, sorry, can you see it correctly?
Yes, you can see your screen now.
Okay, great. Let me also share my video.
Okay. Would you mind turning? Oh yeah, camera comes on. Hi there.
Yes. Okay, so hi everyone. I am Emma Esparza Borges from the Instituto de Astrofísica de Canarias. And today I am going to present our work on applying cross-correlation techniques to JWST data in order to perform atmospheric studies of exoplanets. Oh, sorry, cannot. Okay. Did you see well the change of slide?
Yep.
Okay, great. So for those of you that are not familiar with WEST39b, WEST39b is an exoplanet, hot Jupiter type that is orbiting a solar type star that is slightly smaller than the sun, and it has an equilibrium temperature of 1,200 Kelvin. WASP-39b was observed for the very first time with JWST in 2023. Well, actually in the summer of 2022. And the first science results obtained with the observations of WASP-39b with 3 different instruments of JWST were published in Nature in 2023. And I would like to bring your attention to the results that were obtained with NIRSPEC instrument. Specifically, these results come from 2 different observations using 2 different configurations of NIRSPEC instrument. The first one comes from NIRSPEC Prism, that is a lower resolution observation. And the second one comes from NIRSPEC G395H, that is a higher spectral resolution transmission spectrum of WASP-39b. So in both cases, the authors were able to detect several molecular and atomic species, such as carbon dioxide, water, and several other species. But there was a difference between these 2 results regarding carbon monoxide. In the first case, with NIRSPEC Prism dataset, that, as I already said, has lower spectral resolution, the authors were able to detect carbon monoxide with enough confidence. However, in the case of the NIRSPEC G395H observations, the authors were not able to detect carbon monoxide with enough confidence in order to claim the detection. So in this context, we set out our analysis and we decided to try to confirm the carbon monoxide detection in this second dataset, the highest spectral resolution dataset from NIRSPEC G395H observations. To do this, we took these observations. We only used the observations from the second detector that is called NRS2, and we reduced these observations with the Tiberius pipeline, and we did this at pixel level in order to obtain the highest possible spectral resolution that we can obtain with JWST. And in this way, we obtained the transmission spectrum that I am showing here, and then we focused on this spectral portion of the spectrum from 4.6 to 5 microns. And we did this because this is the portion of the transmission spectrum where we expect carbon monoxide to dominate above other molecular species that are expected to be present, such as carbon dioxide and water. So as I said in the beginning, here I am presenting you the work that we did using a cross-correlation methodology. For those of you that are not familiar with cross-correlation, what we are doing with a cross-correlation is to compare our observations with a certain molecular template and to evaluate the similarity between these 2. So we already have our observations and we need to obtain a molecular template. In our case, as we aim to look for carbon monoxide, we need to generate a carbon monoxide template. And to do this, we generated atmospheric models for a planet considering that its atmosphere is composed only by carbon monoxide. And we did this in parallel for 2 cases. First, we did a template considering the case of an atmosphere of carbon monoxide containing only the main isotopologue of carbon monoxide. And then we also produced a template coming from a line list that contained opacities from all carbon monoxide templates. We used the line lists from HiTemp database, and to produce the atmospheric models, we used the Petit Trans code, that is a radiative transfer code. So to produce these models, we did several assumptions on the planet and on the system. And here you can see some of these assumptions. As I already said, we considered an atmosphere composed only by carbon monoxide. We use the line-by-line radiative transfer mode in Petit Trans that is providing a very high resolution output spectrum. And we also assumed several planetary parameters such as the planetary radius, the surface gravity, and also we assumed an isothermal profile in the atmosphere of WASP-39b. Then, when we have produced our very high resolution atmospheric models with petit retrans, we needed to resample these models in order to match the spectral resolution of our observations. And to do this, we use the Spectres module that is a publicly available Python module. And then we just normalized this lower resolution spectra with a fourth order polynomial fitting. And that's how we obtain our carbon monoxide templates. Once we have obtained our carbon monoxide templates, we have already prepared our observations and we're ready to do the cross correlations. So we cross correlated the transmission spectrum, this portion of the transmission spectrum that I showed at the beginning, where we expect carbon monoxide to dominate between 4.6 and 5 microns. And we cross correlated this portion of the spectrum with these two different carbon monoxide templates. The cross-correlation procedure that we are following is pretty standard compared to the cross-correlation analysis that are normally performed for atmospheric studies. We used a function from PyAstronomy. We shifted our template in the cross-correlation over a range of plus minus 1,000 kilometers per second. And we used a radial velocity step of 6 kilometers per second. And then we obtain as the output of the cross-correlation what we call the cross-correlation function that is evaluating the similarity between our observations and the template. And we converted the cross-correlation values to signal-to-noise ratio units in order to be able to interpret better our results. Here are the results that we obtained after performing the cross-correlation. On the left, you can see the resulting cross-correlation function for the case of the carbon monoxide main isotopolog template. And on the right, you can see the resulting cross-correlation function for the case of the carbon monoxide all isotopolog template. As you can see, in both cases, we are obtaining a central peak that is meaning that we have a detection of carbon monoxide. In both cases, this peak is shifted towards minus 80 kilometers per second approximately. And this is totally fine because this is in agreement with the expected velocity offset, taking into account the systemic velocity of WASP-39 system and the velocity of JWST at the time of the observations. So the first result of our analysis is that we are able to detect carbon monoxide with cross-correlation techniques. And then besides this central peak shifted towards minus 80 kilometers per second, we are also observing secondary peaks that are surrounding the central peak. These secondary peaks are around plus minus 600 kilometers per second from the central peak. And at the very beginning of the interpretation of our results, we were not sure of where these peaks were coming from. So in order to know and understand better what was producing these peaks, we did the correlation of each carbon monoxide template with itself. So we did a self-correlation of the templates. And we also did the self-correlation of the data. So we also cross-correlated the data with itself. And the results of those cross-correlations are the cross-correlation functions that you can see shaded in the back. And as you can see, the light blue cross-correlation function is coming from the template-to-template cross-correlation, so the self-correlation of the carbon monoxide template. And as you can see, the secondary peaks are also present here. So what we are extracting from this fact is that the presence of the secondary peaks is actually reinforcing the fact that the signal is coming from carbon monoxide. And another result that I would like to highlight among our conclusions in our analysis is the fact that we observed that the significance of the carbon monoxide detection was increasing when we were taking into account all isotopologs in our template. As you can see, the increase in the significance is very slight, it's only around 1 sigma. But we think that this is a very promising result for the future that is suggesting that we might be able to perform individualized topological search in the future using cross-correlation techniques. So here are the main conclusions of our analysis. First, as I already said, we were able to detect carbon monoxide in the atmosphere of WASP-39b using observations coming from JWST NIRSPEC G395H, and we did this by using a very standard cross-correlation technique. So we have proved that it is possible to apply this kind of techniques in observations with the characteristics of JWST that are at low mid resolution, around 3,600. And we also suggest that individualized topological searches might be possible in the future. But the very main message that I want you to bring home is that cross-correlation techniques are a powerful and especially a computationally cheap tool that help us to study the atmospheres of exoplanets. And they are much faster and easier to use in terms of computational effort if we compare them with the traditional retrieval techniques that are generally used for this kind of observations. So here I am leaving the QR code that will lead you to the article that we published with this work. And also I am leaving here my contact email in case you want to contact me, and I will be happy to chat with any of you. And of course, I will also be happy to take questions now. Thank you very much.
From the room. If not, I have a question, Emma. So it's Vincent Kaufman here at the front. I don't know if you can see me, but so very typically cross-correlation studies are done at much higher resolving powers. Are there any limitations to using James Webb cross-correlation resolving powers that you've noticed?
Yeah, well, so at the very beginning, we did this analysis as a test to see if cross-correlations worked or not. And what we saw is that they are actually working, and we are able to use them to detect atmospheric features coming from the exoplanet. However, for example, compared to higher resolution observations from ground, we are not able to see, for example, the motion of the planet during transit, just because of the resolution that we are able to obtain with the JWST is not high enough. So I would say that's maybe the main difference compared to very high resolution observations from the ground.
Okay. What is the limiting speed resolution that you can get with the resolving power of about 4,000?
I don't have that number in the top of my mind right now. I will need to do the calculations for that.
Yeah. All right. Thank you. Are there any questions online? I have a question here in the room from Geronimo. If you want to move up to the microphone.
Hi, Emma. This is Geronimo here, Villanueva. Great talk. Question. So you focus on this detection of CO. Have you looked at the other detections? I mean, you mentioned that they also detected water and CO2. I mean, and what about other unknown molecules? Have you looked at other molecules in the same spectra, but other features?
Yes, I'm happy for the questions because actually I have prepared a backup slide for that. Yes, so I have already looked for water and carbon dioxide, and these are very preliminary results. They are not yet published, so please don't share them. But as you can see, we are able to detect very confidently water, and we are also able to detect carbon dioxide. However, we still think that carbon monoxide is a molecule that gets very advantaged of this technique because of the pattern in the distribution of lines of carbon monoxide. But as you can see here, we are also able to apply this technique for other molecules.
That's super exciting. Beautiful work. If there are no further questions, then I would like to check whether Claudia is online. And then we'll thank you again, Emma. That was awesome.
Thank you. Bye.
Claudia, if you can share your screen. Perfect.
Hello. Can you hear me
Yes, we can hear you.
and see? Okay. I'll just share my screen. Thanks.
Perfect. We can see your slides. All right. So Claudia.
Okay.
Claudia's going to talk to us about bringing astronomy into the living room. Please, you can take it away.
Thank you. So good morning. It's really a pleasure to be here with you. I'm connecting from my hometown in the south of Italy, and I'm very grateful to the South African organizers for all the online provisions that enabled me to follow this meeting remotely. And thanks to the SOC for accepting this talk. So I'm going to present the work of myself and a group of colleagues that I coordinate at the National Institute for Astrophysics, INAF, in Italy. Some of my colleagues are actually in Cape Town, so you may have met them at the INAF booth. And we want to share our experience of over 3 years live streaming astronomical events to the Italian audience. In particular, our format, which is called Il cielo in salotto, which translated means the sky in your living room. It's a live streaming format we developed to be suitable for the general public as well as teachers and students. And at this QR code that you will see on the screen, you can find the link to the to a playlist with all our broadcasts. So it all started as also was mentioned in the first talk this morning, 4 years ago during the COVID pandemic. You probably remember when many of us were sheltering at home, then the universe decided to give us a beautiful gift, a rare Jupiter-Saturn conjunction. It was the end of December 2020, right when all observatories were closed to the public. So at INAF, we decided to embrace a science communication format that was new for us at the time. So live streaming from our network of telescopes spread across the country. And actually, it was quite successful. We had around 100,000 views. So we decided to build upon that. Not only because at the time there was still a lot of uncertainty about the evolution of the pandemic, many schools were still offering classes remotely, but also in sight of the future, because this new format enabled us to reach a new audience. So people, families, schools who don't or can't visit our observatories because of geographical distance, because they don't have resources or other reasons. Of course, we also we are aware that viewing celestial bodies through a telescope, but mediated via the screen of your smartphone or your computer, is nothing compared to the experience of looking through the eyepiece of a telescope, especially in an era in which we have this bounty of shiny, beautiful images of planets and other celestial bodies, like the ones we've seen also this morning in the plenary talk from JWST, and many other great telescopes that we have available today, and they're actually available to the public at a fingertip. So we decided to focus on a format that would showcase what we can do at best. So today, since then, we have broadcast 15 events on a number of different topics. These range from the moon, observations of the moon. The moon is always a great classic. Full moon, first quarter, they show, you can see different features. The infamous supermoon, which of course is the full moon close to perigee, which is a darling of the media. So that gives us a huge amplification factor. And then we just we show the moon and we talk about astronomy. And among other events, we broadcast solar eclipses, we broadcast sun observations without eclipses, planets, comets, stars, stellar objects, an exoplanet hosting star once in an episode dedicated to exoplanets and galaxies. So the format we developed today has a few basic characteristics that I'm going to share in case any of you would like to repeat the same experience in your countries. So we usually have one host in a virtual studio. Sometimes we have two hosts for some extra dynamics. We always have at least two different observing stations in different parts of the country because of weather, of course, and weather can change at very last minute. Sometimes we have more. We've had up to 5 or 6. So it's always better. And we always ask our astronomers to take backup observations in the previous days or weeks, depending on what we're observing. Of course, if it's a full moon, it has to be a month in advance, so that even if it may happen that the weather is bad on the entire country, then we always have something to show. We invite a special guest. So usually an astronomer, an expert on a particular topic, can talk about recent results. In a couple of occasions, we also invited best-selling book authors. Our format is very compact. We try to stick to 1 hour maximum. We had longer broadcasts at the beginning, but we saw that they don't work as well as a more compact. So we try to stick to 60 minutes unless there's a special event like an eclipse that really unfolds over a longer timeline. We broadcast to YouTube primarily and Facebook. We're considering Instagram because it's a growing channel. We moderate comments live in the chat because especially when there's several thousand participants, it can be very heated. There can be inappropriate comments. And then from the chat, we also extract live questions that our experts answer live on screen, or we also reply in the chat itself. We script the storyboard in advance, at least to have a rough idea of the rhythm. And we always show what's happening on the sky. So there's always a window, usually a large window showing the celestial phenomenon. At the beginning, we also tried some talk show formats, or there were some presentations with slides, and now we tend to avoid that because what people really are interested in is to see the actual telescope observations live. This is actually based on evidence. So over the past 3 years, we ran a focus group over the same event, so the live streaming of the supermoon. And we asked our focus group several questions and asked them to rate several aspects of the program. Here are the highlights. So whether they had fun, whether they thought they saw the sky, whether they thought they learned something interesting, something useful, and whether they found the content suitable to them. And we asked them to rate these aspects from 0, least satisfaction, to 5, the highest satisfaction. And we asked them the question before and after the broadcast. So you can see the before in blue and the after in red. And after the first broadcast, we had some overall satisfaction, but actually some expectations were not met, especially in terms of having fun or in terms of seeing the sky. So we worked on the format and improved it for the following year. So in 2022, we repeated the focus group and we had some better results. So you see that most expectations are met and the results tend to be skewed towards the right, so the highest satisfaction. And then finally, last year, it was the third supermoon broadcast with a focus group, and the results were even better. So most expectations were met or surpassed. So this gives us confidence that the format we developed is well suited to our audience. In case some of you would like to repeat the experience, some tips on the equipment. Of course, you need a telescope with a digital device. Could be a CCD, could be a digital camera mounted on the eyepiece. I recommend to have 2 telescopes in 2 locations because of the weather. If you have more than 2, that's even better. For some events, we also use a digital camera with a wide-angle lens on a tripod, of course, to show the landscape. That's very nice. For example, when you want to show the moon rising or quote-unquote alignments between planets and other objects. And so it helps people to relate to what they're seeing from their own window. In terms of telescopes, we've used all sorts of telescopes, as you can see in these screenshots with our colleagues in the small window, because on the big window, we try to show what's visible on the sky. So portable telescopes, for example, 20 centimeter are great to show the surface of the moon, to show planets. We've also used, as we have them available, larger telescopes, professional 60 centimeter that you can see at the center, and 1.2 meter, the small telescope of the Asiago Observatory in the right image, both observing the 2023 comet ZTF. And once we've also used the Galileo National Telescope, which is even larger. Of course, you need a camera to broadcast the astronomers taking the observations. It could also be the computer webcam. Most important thing is the microphone. So for live streaming content on the internet, audio quality is fundamental. So if you're investing in something, I recommend to invest in microphones. You need an internet connection, of course, and the live streaming software. We normally use StreamYard, but on several occasions, we've also used OBS, the Open Broadcasting System, which is also great. You need also a webcam microphone and a virtual background to film the host of the show. I'm going to show you later. We've also experimented with virtual studio and green screen, but that's actually not really necessary. What's most important is to have a team behind the scenes who checks the script, that the rhythm is all right, and welcomes guests and the feed on and off, and monitors the chat. In terms of images, many occasions, real-time observations are fine, for example, for surface of the moon, for planets, but for deep sky objects, a real-time image, especially when you have this great JWST and France images, it might be disappointing. So we still show the real-time observations, but we prepare a stacked image from the same telescope taken in advance or even during the live stream to show how astronomical images are made. Here are some experiments with the green screen and 3D models. It's fun, it adds some extra features, but it's not essential. What people really want to see is what's happening in the sky. So these are some statistics of all of our broadcasts. So from top to bottom, the most recent one was the solar eclipse in North America. That wasn't even happening in Europe, and still it was a huge success because the media was talking about it a lot. So solar eclipses allow us to reach most people, together with the very first broadcast of Jupiter-Saturn conjunction, but also the supermoon is very appreciated, and the comet broadcast did quite well also. So what people like best and least from the focus groups, as mentioned, they want to see the live telescope images. They appreciate the possibility to ask questions live to experts and in-depth, clear explanations. Sometimes the explanation can be too detailed, a bit picky, so that's not appreciated as much. The chat, when it gets heated and there's a lot of silly comments, most people, well, the people who type those comments probably enjoy doing that, but others don't appreciate it. And the first broadcasts were a bit too long. The rhythm was a bit slow and ended up too late. So we tried to make it more compact. Teachers appreciate this content a lot, and they use it in the classroom. They either encourage the students to watch it at night, or they show it in the morning, the day after, and it's the single best appreciated type of content from our outreach magazine, Edwin. So to exploit that, we also provided some live streaming activities in the morning on one occasion during the partial solar eclipse that was actually happening in Italy in 2022. And we had 5 telescopes from 5 different cities connected, and we managed to reach hundreds of schools all across the country. And then just a few months ago, we had another morning broadcast observing the sun. with visible and radio telescopes, and we had a live experiment of measuring the diameter of the sun together with the scientists, and most students, as you can see, guessed it correctly. Whether they did the proportion right or they checked it on Wikipedia, it still means that they practice their research and digital skills. So we are happy with that. And with this, I thank you and I welcome any questions.
Thank you, Claudia. Do we have any questions in the room or online? Otherwise, I was curious. So most of the observations take place in Italy, correct?
Yes.
Okay. Has there been any attempt to reach Italians living abroad and see if there's difference in time zones that you could stream these events during the day, perhaps?
No, we haven't tried that. That's a good point. We could also, because of course our broadcasts are in Italian language to reach our local audience. We could think of something with the Italian network of schools abroad, and we also used during eclipses. We have a collaboration with Time and Date, so we also use some of their feeds to show observations from where we are not present. But we're also open to make dedicated broadcasts in English, or in other languages together with local hosts, so that we could exploit this infrastructure that we've set up to also provide the observations to other countries. Thanks for the question.
There's a question online.
Oh, that's for me. Thank you, Claudia, for your presentation. So I have a question. So I know that you're trying to stream all these things, and it's very good. So are you thinking about doing some kind of workshop or training to students for like a couple of weeks that they can get more practice on the data and how they can, for example, doing analysis like what Maria was showing, doing exoplanet stuff or solar system stuff?
Not as part of this program, because this is really aimed at more like primary and secondary schools. But that is something that is being done by a different group at the National Telescope Galileo in the Canary Islands, which is an Italian telescope in La Palma. And it's also something that, especially with exoplanets, it would be interesting to look into, to have a longer dedicated program with observations in which, as you mentioned, students could also play with a bit of data. Or I really liked actually what Maria presented earlier, the proposal to observe a planet, and then of course they could not observe it with JWST, but maybe they could observe it with one of our real telescopes and still get some valuable data. So yes, thanks for the suggestion. It's something that we're really open to expand.
Okay, great. There's some comments in the chat now, but I'm sure you can monitor those from the comment. I think we have to wrap it up here now. So let's thank all the speakers again. And I guess we'll reconvene at 1:30.
I am Xian Shi from Shanghai Astronomical Observatory, and I'm going to chair this session. Right, so before we start, I just want to ask our speakers to keep an eye on the traffic light system over there. So when the green light is on, you're good to speak, and when the yellow light is on, it's time to take questions. And the red light, that's the time's up. So, okay, so without further ado, let's have our first speaker of this afternoon. It's an invited talk by Mahan Khairy, and he will talk about education and outreach in planetary science. Please.
Thank you so much. And hello, everybody. Okay. Just 1 minute. Sorry, it was my shingle. Well, hello, everybody. It's a great pleasure for me to be there and sharing some experience we had in Senegal for trying to develop astronomy and space science, and specifically trying to impact our education and the development of our country using astronomy. And I would like to start with just one number, which is 16%. If I ask you what it could mean in a country like Senegal, 16% could be difficult for you maybe to find the answer. But 16% is the number of Senegalese candidates at the exam called the baccalaureate. So it means that we have only 16% in scientific fields in Senegal for the exam called baccalaureate. It's very, very low. And if you want to develop your country using science and technology, facing the fact that only 16% of candidates are interested in science, it's something very difficult. And this is why we are trying to use something like astronomy, maybe the best tool we ever found to impact young generation in Senegal. And this is why in 2006, I decided to leave Paris and to go in my country, trying to do my best to develop maybe astronomy and space science. And this is why we started by creating in 2006 this association called Senegalese Astronomical Association. It was for promoting astronomy all around the country. And this is a picture of the team which were there at the beginning to start this association. And we use a special occasion, the partial solar eclipse of March 29, 2006, to see that the population were very interested by this kind of events. And this is why we decided in 2006 to create this association. So we start with this kind of equipment, some small telescope to travel all around Senegal. And the first activity was to train teachers in Senegal. If you want to share knowledge about astronomy, we saw that the first step must be to train some teachers so they can duplicate the training in their schools. So this is why we start by training first group, like this one on observing the sun, making some ephemerides and so on. And this is how things start in Senegal in 2006, 2007. And we start moving all around the country. And you have here some samples of activities in some schools all around the country. And we noticed that the students were very interested by learning astronomy and knowing more about the universe in general. So we keep on doing that for 3 to 5 years, since 2008 to 2014, we start a new activity called the Festival of Astronomy of Saint-Louis in the city of Saint-Louis, which was the first capital of Senegal at the north of our country. So we start doing this festival in Saint-Louis, and you have here some samples of training students for the University of Gaston Berger at the north of Senegal, and a lot of discussion with the population about the importance of developing science and technology, but also the importance of astronomy in a country like Senegal. And here you have something very special. We talk with a population used to go, to deal with the sea. Usually they use the stars to navigate, using the sky, at the night to navigate. And it was very interesting to discuss with them and knowing how they use constellation and so on to find their position. And it was a very interesting discussion. So we keep this activity for about 5 years or 6 years. And by this kind of event, we have special occasion to invite some guests like Hubert Reeves, maybe you already know. So Hubert Reeves, on 2009, one of the most famous astrophysicists from Quebec and France, yes. So we received Hubert Reeves in Senegal for 1 week, and sharing a lot of conference and so on. And this is how, the interest start to grow all around the country. And by these activities, finally, you have the chance to attract the attention of national and international press about the development of astronomy we were searching for in our country. So you have here an example of the magazine called The Ciel and Espace, making a very nice article on what we were doing in Senegal. It was in 2012. So, when you start moving from a city like Dakar, which is here, to Saint-Louis for the festival, for several years, people start asking why you just keep on moving on this line instead of going all around the country. And this is why we decided in 2010 to create a new concept called the Space Bus. And the Space Bus was written as a project at 2010. And something specific is that if you try to find sponsor for making maybe a concert, music or dancing and so on, you can have a lot of sponsor. But if you want to find sponsor for making activities in astronomy in a country like Senegal, you have a lot of people, listening to you. Oh, yes, that's nice. That's great. Sounds good. Okay, we will call you back. And nobody call you back. So from 2010 and 2014, we keep on searching for a sponsor to develop this activity. By chance, a wonderful person who was the rector of the University of Saint-Louis, just to become the Ministry of Higher Education, Research, and Innovation. And he just gave me a call. Please, can you come and see me? Okay. And it was then that the minister decided just to give a support for this project. So it was in 2015 that we have the chance to go all around this country to develop the concept of Space Bus. And Space Bus was just something amazing. We just pick up this kind of bus, and a lot of cars like this with all the equipment, and we go all around the country for 1 month non-stop. We travel all around Senegal, and this is the impact of this activity. You have here in many cities the interest of the young generation. For the nights we were stargazing, and a lot of physics, astronomy and physics activities during the day, observing the sun and so on. And it was at those times maybe the most important event organized in West Africa for developing astronomy. It was about 35,000 person met in Senegal directly, and using the television and social media, maybe more than 1 million person touched by this activity. So it was the first edition. And 1 year later, we decided to just make a small version of the space bus called Women in Science. And this is an activity hosted at the Great Theater of Dakar. And we asked to some wonderful person as role model to come and share their experience with the young girls in Senegal, because it was important. If you want to change the destiny of your country, if you want to change the impact of science and astronomy in your country, it is important to talk with young girls. And this is when we ask also to a wonderful person here in the room called Catherine Collenberg to participate to this activity. And it was just amazing to see all these people, you know, listening to those role models. And I think that on this picture, you have another one who was maybe not a speaker, but very important also, Salma Silla, who is also astrophysicist like Catherine Collenberg today. So around 2,000 young girls listening to those role models, it was very important. And, you know, by dealing with this activity, we keep also something very important on mind is to discuss with the parents. You know, usually the young people are very interested in science, but it's sometimes the father or the mother who just decide, no, you are not going to do science because it will take a long time to be a doctor, PhD, and so on. And at the end, you will not going to have a lot of money. So go and find something else where you can find a lot of money. So this is very difficult, and we need to discuss with the young people, but also with their parents about the importance of making science for our country. We are planning to travel again for the second edition of the Space Bus. It is supposed to be from October 15 to the 20th of November of this year. So we are moving, and it will be about 25 steps instead of 17 steps for the first edition. So if you want to participate to this event, you can come and travel all around Senegal with us. It's very, very important. A lot of people we met for the first edition just to come back a few years later saying that we decide to stay in scientific field, or we decide to do astronomy, astrophysics, just because we met the space bus a few years ago, and it can change maybe the destiny of one young boy or one young girl in Senegal. So after these activities, like I said, you catch the attention of the international press, but also international actors like NASA. And one day, one of my best friends just called me and saying that, I met two guys from NASA, Mr. Alan Stern and Mr. Marc Bouy, and they are planning an activity about stellar occultation, which may concern Africa. And they are trying to find someone to give a hand for developing this astronomical activity. So it was for the New Horizon mission. And David Baratou just to tell them that, oh, I know someone in Senegal, maybe who can do something. And this is how the contact started with NASA in 2018. So NASA asked us to hold an important mission for developing this activity, stellar occultation, trying to collect data and help the spacecraft New Horizon to go straight to a Kuiper Belt object called Ultima Thule at those moments, and now it is called Arrokoth. So this is when the president of Senegal, the former president of Senegal, received all the delegation, and most of the people we used to work with for the previous activities I just come to show were in the group, and all this meeting preparing this activity. And this is the whole team receiving by the former president Macky Sall of Senegal. And this is how things started to have impact in your country. You start just going to the schools and discussing with young people. And one day, it's the president of Senegal who accepts to host this mission, and at the end to receive all this delegation. So this stellar occultation helped NASA to have more data about the shape and the trajectory of the Kuiper Belt object Arrokoth. And this is the picture we got from New Horizon on the 1st of January, 2019. It was the flyby of Arrokoth, and it was very nice to see that data is collected from the stellar occultation in Senegal, in South Africa, and in South America also help to define perfectly the shape of this object. So it was a very nice activity, a big success, and a collaborative activity. And what you have here is the second mission. On 2020, NASA just write again through Marc Bouy, saying that we have a nice occultation coming, and it concerns also Senegal. So it will be difficult for us to come because we were at the beginning of the pandemic period of COVID. So are you ready to host this event? If we send you the equipment, I just say yes. You know, sometimes you just say yes, and after you take the time to think about it. So I say, yes, we will do it. So they sent 2 tons of equipment. And this is the wonderful team we work with. Some people from France, Eric Lagadec, Sylvain Boulet, François Collat, Catherine. Catherine is always with us. And it was very nice, you know, with the whole team. And you have some Senegalese people here. I think Abdoulaye Ba is somewhere here also. And it was the second mission for NASA, but for a new spacecraft called Lucy. And it was also a success. Like you can see, it was a very nice opportunity to train young generation in Senegal, dealing with these critical activities to have some important data. And I don't know if everybody can imagine what it means. It's just, you know, dealing with an event which will be just for 2 seconds or 3 seconds. You have 6 months discussing with NASA if it will be possible to do it. 1 month of activity, you know, receiving the equipment and preparing the mission. 5 nights of training directly in Senegal, and just for recording this moment, which is 1 second, you know, how it works. Oh, okay. So it was for this star, and for 2 seconds you will see the star disappear. It means that the projection was good and the asteroid just passed in front of these stars. So we succeed this mission, and this is when they decided at this event to give my name to an asteroid called 1998 DW23, which is now called 35462 Madame Curie. So this is the orbit of this asteroid. And it was a very important moment. And, you know, in a country like Senegal, when astronomy is not really existing, having this chance to name an asteroid by a Senegalese person was very important about the impact you are trying to have on the population, but also the authority. And this is why the president received me to discuss about this decision and send also this tweet on Twitter. And when the president sent a tweet, it finished at the national TV and so on. And you finally catch the attention of the president. In 2021, the last mission, occultation mission for the asteroid called Oris, always for the spacecraft Lucy. And this is also this amazing team with Anne Verbisker, Mike Skrutsky, and so on, working together with the help of someone from Burkina Faso, because it's very collaborative, Marie Corsaga, and we held our third mission, occultation mission for NASA. This one was very nice, and it was a big success. You know, at the beginning, Mark just told me, you will receive 10 telescopes, and if only one telescope can catch the occultation moment, it will be a success. It was not easy, but at the end, all the 10 telescopes got the critical data we were searching for. The last telescope didn't see the occultation, but it was also a good information. It was just meaning that the size of the asteroid was maybe less than we were expecting. So it was a very nice mission. And at the end of this mission, we decided to create a new website called L'Astronomie Afrique with the help of the the French Astronomical Society staff. We decided to create this website to share astronomical information for all the continent, but in French. It was important because there was some information missing for French part of Africa. One day I received, after all these events, I received a call from a producer who was preparing a movie on how they are using Gaia data to predict occultation, stellar occultation with data from the satellite Gaia. And they asked to NASA and to Mark maybe if they can do something for this movie. And Mark asked them to make the movie on what we are doing in Senegal. And it was a very nice moment. And this is...
In West Africa, astronomers are on a mission. This is very important.
If you don't get the data at the right second, you don't get the data ever.
Discover a history of African astronomy.
Wow, it's incredible.
And one scientist's dream for the future.
I believe space is for everyone.
Star Chasers of Senegal on Nova.
Well, so this is the trailer of Star Chasers of Senegal. You can watch the movie if you live in the US. And just 1 month after the first screening in the US, the president of Senegal accepted with 4 ministers to host the screening in Senegal. And this is the moment of what happened in Senegal for the first screening in this movie.
Senegal, sukaɓe Senegal, oɗon keewineede, oɗon dari hande moɗon, ɗon toyno janngo meɗen, yo Allah yetten fandare, kono mbaɗi kende ngaraje maram kay.
So maybe you're wondering why Madam is sharing this guy singing. Have you have the chance to see Black Panther, the movie? Yes, Wakanda. Yeah. So it was Baba Mal singing on the movie, a Grammy Awards artist from Senegal. And the impact is to find maybe some good ways also to achieve your goals, and using some artists like Baba Mal was very important also. So at this event, the president of Senegal decided to create the Senegalese Space Agency. And people were fighting for a very long time to have a space agency in Senegal. And the achievement of all this effort from 2006 was to have, at this moment, the decision of the Senegalese president to create our space agency. So it was the most important step from the beginning. And the movie is going on. We have received a lot of awards for this movie. But the most important point is that we now have a space agency in Senegal, and we can do maybe more efforts to impact the development of space science and astronomy in Senegal. And here you have the short definition of what it means for Senegal to have a space agency. We are in charge of designing, implementing the national policy and strategy for the study, research, training, promoting, and the development of space activity in our country. So it means that we are going to work on a long program based on the Agenda 2063 of the African Union, but also trying to be connected at the Sustainable Development Goals. So quickly, if you watch this dashboard from the United Nations of last year, the dashboard is on 2023, showing how people are making effort and how countries are trying to reach the SDGs in their development plan. You can notice that if the blue is very intense, it means that the country is doing a lot of efforts. And the part of the world where we have to do a lot of efforts, stay Africa. If we look back in 2009 and 2015 about people or countries using satellites, having their own satellites, countries having their own space agency. If you match these layers, these three layers, you will see that usually it will be the same areas which are maybe making efforts in space science, which are the same leading the achievement of the SDGs, and Africa still maybe the part of the world where we need to do a lot of efforts. And this is why from 2018, they decided to create the African Space Agency to make Africa maybe aware about the importance of using space science. And you have a lot of satellites launched from the continent. We are about 40 satellites launched by Africa this last 20 years. And in Senegal, we are planning to make our priorities on these 6 points. The first one will be Earth observation, education, research, science, meteorology and climatology, marine surveillance, communication for disasters and isolated areas, defense and securities. It means that we are going to work as a cross-functional agency. We are going to work with all the priority of Senegal. Stay focused on the SDGs. What we mean is to try to develop interaction between the private sector, the government, and to maybe at the end develop a space and digital ecosystem. We have a lot of activities for the digital ecosystem in Senegal. We are trying to move them on the space sector. So if we can do so, we will have a very dynamic space ecosystem. And at the end, we can produce services. By using these services, we can impact the SDGs. And this is what we are trying to do, to show to the government and to show to the population that using astronomy can be a very nice and very good tool to motivate people in doing science, can be the perfect tool to impact the development of space science. And by developing this space science, we will impact the SDGs. Your priorities like security, education, health, and so on will find solution by using these services we are planning to develop. This is what we are working, and to go quickly, so it will impact all the life of the Senegalese people for oil and gas surveillance, the navigation, the security, hospitals, and so on. We will try to develop a lot of services. We have to sync service, talk service, and produce services. Since the beginning, or I have just less than 1 minute, since the beginning, so all this part is already done. The space agency is created, installed, benchmark is starting. We start our strategic plan for the 10 years and the communication. We are working on the launch of the first satellite, which is already finished, and it will be for this year. We are going to start the second satellite, the first constellation on 2025, launch it, the second satellite on 2027, and the first constellation will be ready for 2028. So we are planning to build our first observatory in Senegal. It is on the road. I just finished to have a support for achieving, for getting the first telescope. It is already okay. And we are planning to build this observatory in Senegal from 2025 next year. So it is already planned. And this is the kind of setup we are going to use. At the end, we are going also to build the first assembly building for developing our microsatellite in Senegal. It will be the facility you have here for assembling, building, testing, and developing microsatellite. And to finish, this will be at the heart of a new project we start, and the president is concerned by this project. It will be a Senegalese project, not the space agency only, but the state project of building the Senegalese Space Valley. And all the economic activity will be hosted in this place. You will find the headquarters of the space agency, the building for microsatellite, reception data center, research and development center, an exhibition center, innovation laboratories, an observatory, a lot of accommodation, and so on. So this new city will be a sort of Silicon Valley you have in the States, or what Toulouse means for Europe. We are planning to host all the economic, innovation, technology activities in this city of Senegal, and it will be maybe the most important project. If we can do so, you can have a young generation dreaming about astronomy in their country, having the chance to be trained in their country and to work in their own country, and it is very important. We are not searching for just launching one satellite, but to develop a very long-term activity in astronomy, and this is what we are planning to do for the next 10 years. So it is supposed to be the end. It was a great pleasure to share with you this small part of what we are doing in Senegal, using astronomy and trying to impact our education and the development of our country. From my part, at the end, I will start before the end of this year a foundation called by the name of the asteroid. And we are going to try to find some means to help young generation. to have the vocation in astronomy and space science for years coming. So this is what I would like to share with you. If you want to give a help or to participate to the development of all this project, you are pleased to welcome in Senegal. Thank you so much for your attention. Yeah, that's perfect.
The next speaker will be online. So Liton Mayonda will talk about linking gas giant atmospheres with planetary formation constrained by JWST observations. Do we have the speaker online and sharing the slides? Okay, looks good.
I'm online here. Yep.
Could you share a slide? Open the slides.
Is my slides visible?
Yes, yes. Please go ahead.
Okay. First of all, thank you, organizers, for inviting me to give this opportunity to talk about this work. So today I'm going to talk about linking gas giant atmospheres with planetary formation and how to constrain atmospheric composition of some of the gas giant which has been observed by Hubble Space Telescope and also recently by James Webb, and how to link their composition with their formation. So this work is done with some of my collaborators who are listed here. I think this is something that we have already seen. So the exoplanets field is now going through a revolution where we are detecting different classes of exoplanets. So far, more than 5,600 exoplanets have been confirmed, and their physical parameters like mass and radii are different, and they vary across full parameter space as compared to what is seen in our own solar system. So the diversity, goes from observing, hot Jupiters to cold gas giants, and we are detecting planets almost every single day. And these planets are diverse in their own nature. And now with the arrival of James Webb, we are characterizing their atmospheres with better sensitivity and with more information. So these atmospheres are key to understand the formation and evolution of these planets. So today in my talk, I'm going to talk about how to make fast-order approximation for some of these planets to get the idea about what might have happened for these planets during their formation. So the field of atmospheric characterizations is largely built upon two fundamental themes. One is understanding the thermal structures, chemical dynamics, chemical abundances and dynamics of the planetary atmospheres, which essentially give us a constant about the planetary physics and chemistry. And at the same time, the planetary composition gives us constraints on understanding how these planets are formed in the disk around young stars. So, and if you really want to understand how these planets are formed, then essentially we need to go back in time and we have to understand the evolutionary process which have started from diffuse molecular cloud, where everything is in form of gas and dust, and this gas cloud collapses to form protostar, and then eventually you form a disk, and these disks are the places where most of these planets are formed. The question then arrives, how does the composition of the disk incorporated into planets, and what physical processes determine the composition of the planetary cores in the atmospheres? So essentially, if we really want to understand formation from the atmosphere, protoplanetary disk is the phase where we need to go back. So recently, we have looked into diverse range of Jovian planets, which varies across their orbital periods and mass. Essentially, most of these Jovian planets, if you can see, we see their diversity in terms of their temperature distribution and also mass. And if we look at the transmission spectrum for this some of these hot Jupiters that we have considered, like which is mentioned here, hat P12b to hat P1b. Their transmission spectrums are different, and these differences could be attributed to different compositions that that is present in this type of atmospheres, and this difference in composition could lead us to theory of different formation. So in order to explain this formation, we have for these subclasses of gas giant that I have shown, we have used our in-house formation retrieval package called Pegasus, which is essentially a disk model, which essentially simulate disk environment by by solving disk physics and chemistry simultaneously and fitting the observables. So these observables could be linked to planet formation, but at the same time, these observables could be linked to the atmospheric composition. If we are assuming some of these gas giants are formed through core accretion mechanism. So we have, as I mentioned, we have looked into 5 of these planets: WAS79b, WAS43v, WAS 18b to WAS12b. And this class is essentially goes from hot Jupiter to ultra hot Jupiter. There are detections for some of the species through low resolution and high resolution spectroscopy from ground and space, and this is the flow of the work that we have been doing. So we have the transmission spectrum, which essentially observed with HST, and soon this these systems will be covered with James Webb. So we have the transmission spectrum, and this transmission spectrum, used in our in-house retrieval code called Nexotrans for atmospheric retrieval. This atmospheric retrieval gives us, measurement of the atmospheric C-bio ratio, bulk C-bio ratio essentially. This C-bio ratio are fed into our formation model, which essentially is used in the background to with different physical and chemical condition and different chemical abundances. With that, we get the spatial and temporal variation of carbon to oxygen ratio, and this carbon to oxygen ratio is compared with the observed or retrieved C-bio ratio from the atmospheres. And with this C-bio ratio, we retrieve what might have happened in the disk and what was the formation conditions. So here I am showing radial dependence of radial and vertical dependence of C-bio ratio for some of these planets. So essentially here, if you see, if we start for a protoplanetary disk with initial C-bio ratio of 0.1, which is very low, and if we assume most of the materials that you see in the disk are inherited from the very early stage, if we recall the different stages of the planet formation. So by early stage, I mean when we are considering the molecular cloud stage. So if we consider initial ratio of initial carbon to oxygen ratio in the disk of 0.1, and if we vary this initial carbon to oxygen ratio across the across different radius, so this is the distributions that we get across the protoplanetary disk. And we can see for some of these planets, the distributed C-bio ratio are fit at different locations of the disk. So for example, WAS43b, then WAS121b, WAS12b, all of them are tracing the outer part of the disk, outer part of the protoplanetary disk. And if we summarize this, spatial distribution, so essentially, the Z-trip, C-bio ratio, which goes from very subsolar C-bio ratio to supersolar C-bio ratio from 0.3 to 1.5. After running our retrieval using Pegasus, what we can see for most of this planet, we are tracing the very low temperature outer disk regions, essentially. So the temperatures are mostly tracing the region which is in between CO2 and methane snow lines, and in order to produce the observed C-bio ratio, which is retrieved from the observations, we need to have diverse set of chemical or chemistry needed in order to reproduce the observed composition. So the reset means the disk that we are observing, which was best fitted to the observed C-bio ratio, needed to have chemistry which is completely reset. So all information from earlier stages of the planet formation was lost. If the second planet, we need to have both. Essentially, that means like we have a disk chemistry and essentially also chemistry coming from the very early stage of the planet formation, and evolution. So for these planets, we can retrieve the location in the disk and also the physics that was representative of formation for this planet. So this model works in the retrieval mode. Now, what about if we think about forward modeling part? So we have taken the same model and we looked into in a forward modeling perspective. So we look into this planet HD209458b, which is a favorite planet for most of us. So this is the two different type of temperature pressure profile was considered for this planet. So blue line represent this planet has a TP profile which is with thermal inversion, and orange line representative of without thermal inversion. So essentially we have considered two different TP profiles for this planet, and we looked into the mixing ratio profile for some of the volatiles, which essentially controls carbon to oxygen ratio together with nitrogen to oxygen ratio in the disk. So here, what we are showing, if we consider disk where planets are forming, and the disk is in an environment of low ionization, and the planet has accreted most of its gas at 1 AU, then this is the expected chemical abundances or mixing ratio profile for the planet atmospheres. And then if we looked at the grids of transmissions spectrum, so here what I am showing, if we assume the HD209458b has accreted most of its gas in the disk, around 0.5 AU, 1 AU, and 5 AU, and 20 AU, with the environment where cosmic ionization is dominant, and most of the abundances in the disk are in the form of molecules. So that means the disk has inherited most of its molecules from the early stage of the planet formation. That means even before the disk was there. Then we get to different diverse transmission spectrum which are dominated by different volatiles like CH4, O2, HCN, and in some cases some of these features are missing. At the same time, if we assume the disk is going through low ionization and has lost all information from the past, so essentially the disk is going through a reset environment, and the chemistry that we see is just representative of the disk, then this is the expected transmission spectrum for this planet. And again, the same thing was done by assuming the planet has accreted most of its gas at 0.5 AU to 20 AU. So now when you have these grids of transmission spectrum, now if we fit that with the observed with all these grids of transmission spectrum, if we fit with the observed JWST spectrum, the question that we are asking whether this spectrum is dominated with water, and if it is dominated with water, and if it has CO2 features, then it is representative of a disk environment with carbon to oxygen ratio of 0.5, and the disk has inherited most of its material from the early stage. But if the planet has dominant water features but without CO2 features, then it is representative of low ionization environment, the disk with subsolar C/bio ratio. So essentially, with the grids, we have all possible formation sequences which can be compared with the different formation history for this type of planets, and could be used to infer planet formation history from the compositions. Of course, this work has some limitations, and because one of the main limitations for this work, this retrieval relies on the assumption that core accretion is the primary pathway for planet formation. And so of course we are not considering migration. So now we're in the process of adding migration in the model. So essentially with that, we can also show how does migration plays a role in retrieving this formation. But one thing very clear, as I have shown in my previous slides, most of these planets are formed, most of the planets are from the outer part of the disk. But since we are observing very close to the central star, so essentially that means you need, some form of migration, for these planets, But C by ratio is not only the full part of the story, but we also need other measurements, other elemental abundances, bulk elemental abundances ratio. With GEMSWAVE, with a higher sensitivity, we expect to observe other, chemical molecules in the atmosphere. For example, ammonia. With the detections of CO2, if we detect ammonia, then we will also have good constant on the nitrogen to oxygen ratio. For some of this disk, it is expected like we'll be able to observe SO2. So essentially having multiple constant in terms of carbon to oxygen ratio, nitrogen to oxygen ratio, and carbon to sulfur ratio, will be able to put better constants through accretion, through core accretion method, and by adding migration into the picture. Also, I would like to add here, this has not yet been, started for some of these exoplanets using GEMSWAVE, but it has already been, done for, for some of the brown dwarfs. So we started to see some of the carbon isotopes in some of the brown dwarf atmospheres. So essentially, if enough integration times was provided, and if we get good constant on the isotopic ratio for different elements, it will provide more robust constant. So essentially having carbon to oxygen ratio together with other elemental ratio and isotopic ratio will provide much better constant in terms of formations by measuring atmospheric compositions. With this, I'd like to end my talk. I'm happy to take any questions.
Okay. Thank you, Lytton. Yeah, again, we don't have time for questions. So let's move on to our next speaker. The next speaker is Salma Salih, and she will talk about using score-based diffusion models for correlated 1/f noise reduction in JWST data.
Okay. Hi, everybody. Thanks so much for having me. It's a pleasure to be here. My name is Salma. I'm a first-year master's student at the University of Montreal in Canada. I'm supervised by Dr. René Doyon from the Trottier Institute for Research on Exoplanets and Dr. Laurence Perrault-Levasseur from the SAIL Institute and the Quebec Mila Institute for AI. So yes, I do AI. I use machine learning for my research. I'm hoping to convince you that machine learning is not just a fancy buzzword, that we can actually use it to do some really cool science. Okay. So because my project is so interdisciplinary, I'm going to spend most of the talk just giving a background of what kind of research I'm interested in and how machine learning can be used for that. So I'm interested in noise, and I know that doesn't sound very interesting, but bear with me, it'll get really cool. Noise is the bane of pretty much any astronomer's existence because instead of getting nice, pretty images like this, if you've got a lot of noise in there, it can end up looking something like this, which doesn't look too bad for like big features, but if you zoom in, you'll notice that you lose a lot of very small features that you're interested in, like these tiny stars over here. Yeah. So we can think of this another way, just mathematically. So if what you're seeing is, if what you're interested in is f at x, which is the ground truth signal, then when you add in the noise, you've got eta. So you see is a combination of the two. And if we're dealing with a Bayesian framework, so I'm sure you're all familiar with Bayes' theorem, what we're interested in is the likelihood, which is the probability of that what you're seeing is described by a given set of parameters that describes the underlying ground truth signal. Okay, so if we go back to noise, if we're dealing with just simple Gaussian noise, then it's actually pretty easy to deal with because we already have a nice mathematical equation to describe that. And so if you want to get to what your ground truth is, it's fairly easy to get a distribution over the true signal values. because you have a mathematical description. Now, I want to just emphasize here that we can't just subtract out noise, that we are limited by our instrumentation. It's called the photon noise limit. So we are limited to that. But if we know the distribution, then we can get as close as possible to that limit and extract as much data as we can, as much information as we can from the data. Now, you probably guessed where I was going with this. Unfortunately, we have to deal with a lot of non-Gaussian noise in the type of science that we do. And I'm interested in exoplanets, specifically transit spectroscopy. So I look at spectra of stars, specifically when the planets are transiting in front of the stars. So this is an example of a spectra. This is what we want to get. Now, I have to stress that this is just a simulation, because if this was real data, then my whole talk would be obsolete. So this is what we want to get, but what we actually get is something like this. So we get a lot of noise thrown in there, a lot of cosmic rays, things like that. And you'll notice, you can tell by eye, it's not Gaussian, right? So we see a lot of these stripy structures here. Okay, so it gets even more complicated when you factor in other sources of noise that are thrown in there, like, so we have it's called 1/f noise, correlated noise, the stripy structures, but we also have bad pixels, dead pixels, cosmic ray hits, epoxy void patches, which are instrumental effects. So all of that, we have to figure out a way to describe this aggregated sources of noise so that we can get as close as possible to that photon noise limit. So I just want to put into context why this is such a big problem, especially for spectroscopic data and especially for the nearest instrument on James Webb, the near infrared and slitless spectrograph. So when we do transit spectroscopy, what we're interested in is the measuring the flux of the star when the planet passes in front of it. So we get this transit, and we're interested in this transit depth here. So this is an example from Madhousen et al. 2023. This is one of their light curves, and here they've plotted the stellar spectrum, and you can tell, like even by eye here, that at longer wavelengths we see there's quite a bit of noise in there. And when they plot their precision and the expected precision, we see it doesn't match up. So it's actually, their precision is lower than what we would expect for an instrument like this. So it's clear that we're not able to extract all of the data that's in the image that we could possibly extract. And what we want, what the end product that we want is a transmission spectrum. So something that looks like this, where we plot transit depths over many different wavelengths, and you'll get like bumps here and there, which would tell you that there is a certain compound in that atmosphere of the planet. And again, we can see that the error bars are larger than we would expect them to be at longer wavelengths. So there are classical methods of dealing with this, but clearly, even after the data has been processed, it's still not good enough. So what's the solution here? Well, luckily, we have a lot of examples of this noise that were taken during the commissioning phase of JWST. And so what we can do is, instead of trying to correct for it, like on the image level, we can try to learn the distribution through a data-driven method, which would be where machine learning comes in. So that's what I'm going to talk about next. Okay, so I'm not sure how familiar people are with machine learning, but I want to give a brief overview of what a neural network is, because that's the heart of what this is about. So this is a nice simulation that my professor Laurence made to show kind of how a neural network works. So if you have, let's say, an image of a lensed galaxy, and you want to learn certain parameters from there. So what the neural network does is it looks at different local regions in the image, and then it associates a weight with that, passes that to like the first layer of the network. And each node in this network applies an activation function to that weight, and then spits out an output. And the more layers you have, the more subtle features you're able to learn in the data. And at the end, after the network has finished learning, what you end up with is the outputted, the learned parameters from your data. So we can easily apply this to learn that noise distribution. Now, it's difficult to learn the probability distribution itself, because you need to know the normalization constant, so you need a lot of localized information. It's instead much easier to learn something called the score, which is the gradient of the log of the probability. That just eliminates the constant entirely. And what it is it's just like a vector field that points in the direction of your distribution. And that's sufficient for what we're trying to do. Okay, so there's a specific machine learning model that we can use to learn the score. It's called a score-based diffusion model. And all it is just a fancy neural network. And so what we can do is it's a generative model. So what that means is if you give it, let's say, images of cats, and it goes through the network, it's going to spit out new images of cats that are not duplicates of what you gave it, but instead it's been able to learn that distribution and then sample from it to generate new examples of cats. So in doing so, we're able to learn that score. So what some of my colleagues did at Ciela, they came up with a method called score-based likelihood characterization, or SLIC. And so what they did was they trained a diffusion model on images of noise from HST and GWST, and they were able to generate images through the diffusion model and hence learn the scores. And then what they did with that was they applied SLIC, which is essentially just a Langevin sampling algorithm that incorporates the scores in order to fit for the parameters that they were interested in. So they were looking at lensed galaxies. And so in this corner plot here, you can see in blue the results from just regular MCMC sampling, which I'm sure you're all familiar with. And then when they incorporated the scores, they got the gray contour plots. So it's much more precise with when we incorporate the scores. So clearly, we have a machine learning method that works pretty well to be able to learn the distribution of the noise. So now I want to explain kind of what I'm trying to do with regards to its applications to transit spectroscopy. So, okay. So what I've done so far is I've trained my own diffusion model on images of nearest noise. So this is an example of a typical dark image where we have all of those correlated noise structures with some cosmic rays and a bunch of other things in there. And so after I trained the model, I ended up with some nice generated images. You can see it's been able to learn it pretty well. So that tells me that it's learning the score or the log of the gradient of the log of the distribution quite well. Now, of course, we can't just rely on the eye to make sure this is correct. We have to also use statistical tests. So it's not quite there yet because it's still missing some like high dimensional features, but it's almost there. And then, so what my project really comes down to is just solving Bayes' theorem, which is this right here. Okay. So, and because, like I said, we're interested in the score only, that kind of gets rid of the evidence entirely. And this is what it really all boils down to, is the score of the likelihood and the score of the prior. So the score of the likelihood I can get using SLIC. So just training that diffusion model on the noise and then sampling from that. And then the score of the prior I can get by training a separate diffusion model on priors, which are just simulations of the underlying true signal. So what I've done is I've generated many, like thousands of examples of these spectra that don't have noise, using like different Phoenix stellar models and PSFs. And then that's what I'm training right now. And then I have my noise model, which I've already trained. And so that's all I need in order to be able to get a distribution over true signal values and be able to sample from that. Once I have that, all we really need to do is sample from that posterior, and then we'll be able to have realizations of what the true signal is without any of this noise. And the idea here is that that should get us back down to that expected precision so that we are extracting as much information as possible from the data. We've poured billions of dollars into these telescopes. We have to make sure that we're getting right down to that limit. Yeah, that's it. Thank you so much.
So fascinating talk. Thank you. My question is, you've trained the expected data, the observed, on models.
Yes.
And so you're expecting your observation to look like one of the models.
Exactly, yeah.
So if the actual planet doesn't agree with the model, won't your method sort of try to make it look like one of the models?
So like
So say, you're training on all these model atmospheres.
Yeah.
But in truth, we find something we don't expect, phosphine, to pick a popular one of the days.
Okay.
Would your fit specifically, not look for that line and therefore not see it?
That's a good question. I think like because like most of the information is actually contained in the likelihood because it's where your data is. So the prior, I imagine, would not have like a huge impact. So I mean, obviously we try to make it as wide as possible by having like as many different stellar models as possible. But the idea is that because your data is contained in the likelihood, that this would win out essentially.
All right, thank you.
Yeah.
Our next speaker is Vincent Kaufman, and he will be talking about observables of 3D atmosphere and surface effects in JWST observation.
Yes, thank you. It's an honor to be here. It's been a great audience, a great set of talks, and it's a true pleasure to be here today. Yeah, so my name is Vincent Kaufman. I'm a research scientist at NASA Goddard Space Flight Center, and I do a lot of work with the Planetary Spectrum Generator team. And I wanted to show some updates about what we've been doing to model 3D atmospheric and surface effects over the last couple of years. So why are we want to study 3D planets? Well, my impression is that planets are not 1D object. A 1D approximation is in fact a really bad approximation for a planet, particularly with its atmosphere. If you consider planets in the solar system, as you can see here, I have a couple of highlights here, but it's clear that none of them are homogeneous. All of them have clouds, and in order to correctly model these clouds, we need to consider the 3D effect, and we essentially need to know how to model this correctly. And on top of that, the abundance of molecules varies strongly with the position and even with height in atmospheres. And as we'll see later, that makes a big difference, particularly for the detectability of molecular species. Obviously, there's also variation in ground cover, as you can see, mostly for the Earth. And then I'll specifically mention clouds here, but they have a critical importance in the atmosphere in terms of the energy balance, composition, and detectability of molecular species. So in order to model this correctly, we need to be able to incorporate these 3D models in our simulations. In order to interpret the data, we need to be able to model it, and for that we've undergone a couple of steps to try and start validating the model that we have. I want to highlight here, particularly in this case, we're looking here at the wavelength in micron. Sorry, the labeling is off here. And we're looking at spectral radiance. But if you're considering a planet like TRAPPIST-1e, it's a tightly locked planet. The front of the planet is very hot. The backside is very cold. In the visible part of the spectrum here, the difference isn't so bad when you do a 1D versus a 3D model. But particularly if you consider the infrared part of the spectrum where we're looking at emission, the thermal black body is so much hotter at the front that the average temperature of the planet, if you consider that for your models, you're going to be really far off in terms of the emission from the planet. So that's sort of part of the motivation. Why are we doing this, and why do we need to do this, particularly for studies in the infrared? Now, what we've been undertaking here is we wanted to use the Earth as an example planet. We have a lot of spatial information from the Earth. We have a lot of information of the atmosphere of the Earth, information of clouds of the Earth. So the Earth is used as a template spectrum or template model here to try and understand what we need to do to correctly model this. Just a quick overview here. 3D effects for eclipse measurements are relevant because you're looking at emission and direct light from the planet. and in transit as well, the 3D effects are still relevant. We won't talk too much about that here, but one of the sort of really pushes into exoplanet atmospheres and the study of planets is the use of global climate models or 3D models of the atmosphere. There's a massive amount of heat transport that takes place in an atmosphere. They're relevant for formation of clouds. We were talking about mass transport, oceans, currents, changes in sea ice, land. All of those things we can now model, and we can apply the 3D models essentially to study exoplanets as well, which is one strong motivation to really start considering these kinds of observations and simulations for the observations of exoplanets. So that's what we've been working on to really. We have all these 3D models, right? There's plenty of studies out there. Thomas was talking about it earlier, and it's something that people study a lot. What is happening with these planets when they're tightly locked? How does the heat get distributed? What is the effect of that on the observables of the planets, right? So where do we find clouds, and how do we model these correctly? Right. So we wanted to use Earth as a laboratory. It's a complicated planet. There's complicated cloud structures here. We're looking here at an image of the Earth from the ISS down at the Atlantic. And I find this image fascinating because we're looking here at so many different types of clouds, different cloud structures. We're talking about several kilometers of cloud height, and how do you incorporate this, right? Because if you're thinking about simulating this as a 1D atmosphere, then you're going to be, okay, well, we have a number of cloud particles or a certain amount of mass of cloud particles. How are you going to spread that over your spectrum, right? So that's why you really need to consider the full three-dimensional structure of the atmosphere. And obviously you can bring that down to a certain granularity, but you do need to consider all those steps in order to get to the right observables. A little bit of details here. What we've been doing is we took monthly average ground coverage from the MODIS database. So it's a series of satellites that get reduced into a database which tells us what's the ground coverage, what is sea ice coverage changing to, which looks like this. So this is an atmosphere or planet without atmosphere, and you can see variations in ground cover as a function of time, and you can see the subsolar spot here and in the reflection from the ocean. We're taking water, O3, pressure, and temperature in a three-dimensional cell. So for each of the square pixels that you see here, we have a full atmosphere with 72 vertical cells. And this is taken from the MERA2 database, which is a retroactive climate database. So it takes in all the satellite information, basically backward runs a GCM model to reproduce the observations, so that we know that each of the abundances are consistent with what's happening on the Earth for real. We took liquid and ice clouds abundances for each of these cells. And then, so that looks like this. So we have the Earth here. This is the 3D file uploaded in the planetary spectrum generator. You can see the abundance for each of the different type of clouds for one layer in this image here. And then we studied some arrows as well, but I don't have time to go into that in detail here. Okay, so quickly to the results here. So there's two images here. On the right, we see observations from the Earth taken from L1. So we're looking at the permanent day side, or the permanently, or it's permanently stationed to look at the day side of the Earth. And on the left here, we have simulations for the exact same timestamp. So that's where the cool part of the data comes in, right? We have NASA collects all this weather data, and we can use that weather data to reproduce the images of the Earth. So I would say when we finally got this to work, and there was a lot of tweaking involved, trying to figure out how to correctly incorporate clouds, because you're dealing with all kinds of spatial effects, right? Because you have very thick clouds centered in a corner of your pixel, and you spread out that material over your entire pixel, you're going to have basically an opaque pixel, right? So when we finally got this to work, we were pretty excited, and this is an image I'm always happy to show. Obviously, there's still some things that we can work on. So there's difference in ground coverage on a very small scale, but considering we only use 5 type of ground coverage, I'm very happy with the way that this looks. We also simulated images from geostationary satellites. This is a Japanese weather satellite that permanently looks at the same spot on the Earth, and it takes pictures every 10 minutes mostly for weather events. We thought this was a really nice challenge to try and figure out what the Earth looks like under different phases, essentially. particularly when you're studying exoplanets. Obviously, you're going to see planets at various phases. So hence we wanted to consider these observations. And as Geronimo in the back can confirm, we've definitely had some challenges with the very extreme angle interfaces where the radiative transfer is really, it's really like creaking at its boundaries, where you have to deal with angles that are just not very well parameterized using a whole bunch of cosine functions, essentially, right? So then the next step, the way that I want to lay this out, right, we do the spatial variations on the one side, where we're looking at our simulations and we're looking at the images. Again, there are challenges there, there are limitations there as well. But the other aspect of this now, we want to look at the flux, right? So it's one thing to make the images look alike, and you can trust me when I say that we didn't have to scale any of the images to match the colors. But the real proof, I would say, is when you're actually looking at the spectra, right? Like the eye is easily fooled, as we know, but spectra and absolute numbers are impossible to, or much harder to fake anyway. So that's what we're seeing here. So here we're looking at the wavelength in nanometer and the albedo, or the reflectivity of the Earth. The full lines are models, and the dots here correspond to very specific bands across on the Discover Epic observatory. So that's the one that's looking down on the Earth. So we found that in the past these images were scaled, they were calibrated. The flux of each of these points is well calibrated, and you can see that with the exception of 3 of these lines here, and we'll talk about that, the intensity of the spectra are very well matched. There's some limitations also in the reflectivity of the vegetation red edge. Considering we're using a single abundance for forest and grass, that's not too bad either. But anyway, we were very happy when we saw this match, and it really proves that the model reproduces the 3D object very well. So we're working on the next steps now. Obviously, we're not done yet, right? There's improvement to be done. We wanted to study the spectral features and sort of apply this to observations, right? Now that we have these spectra, we can integrate the bounds, figure out how detectable these signatures are. So this was more done in the context of Habitable Worlds Observatory, and there it is. The image that we're looking at here now is the Earth now placed in quadrature, and we're integrating the bounds of these molecules here. So we're looking at O3, we're looking at O2, and at water. These are sort of the characterizing gases that you can quantify in this spectral range. And these are, we heard this morning, especially O2 can be a very, very interesting biosignature for determining the climate states and potential habitability or even inhabitation of exoplanets. So what we do now is we apply noise models. We've just heard from Selma about how our observations are always challenged by noise observations. So I don't have to go in detail that. Thank you for that. But if we now imagine that we are looking at the Earth from a certain distance, and we want to quantify how likely it is to detect these signatures after observing a planet for a certain while, we can now apply the models that we have. We know we have a 3D atmosphere, a 3D surface, and we can see how strong these signals are and how much they vary as a function of changing the orientation of the Earth. So what we're seeing here now is we integrate these features as they were colored in. We have what we call the equivalent width, and we have time here on a logarithmic x-axis, and we have the integrated features here shown. The crosses are without clouds, and the circles are, sorry, the other way around. The crosses are with clouds, the circles are without clouds. So what we see here is we have the three different molecules, right? And the stronger the signal is, the shorter the observational time required to find these signals, which makes sense. But I don't want you to focus on the absolute numbers here. That really depends a lot on what instrument you're using, what telescope are you using. But the interesting part is the variation, right? So if we're looking for the specific O2 feature, let's go for the O2 feature here. Sorry, the color came out pretty crappy here. But if we're going about for the brightest, most extreme cloudy case, we see that we only need about half the time to observe this feature as we do for the less bright feature. So that's just something to keep in mind. This is where the 3D variations of the atmosphere and the surface are really coming into play. Then we're talking about the next steps, right? We're talking about this is a James Webb session, so obviously we need to verify this in the infrared, which is what we're working on now. There is an infrared mission that looks at the Earth, emission of the Earth in the infrared, and what I've been trying to do is verify our models against that observatory now. And what we can see here is I was taking essentially two different locations here, a cloudy patch and a non-cloudy patch. And you can see that we're now looking at emission of the Earth. So this is, sorry for the confusion about the axis here, but now we're talking about wavelength. It's a measure of energy, right? You see the white spectrum is the emission of the Earth. Blue is the curve that corresponds to the observed data. You can see that we're getting the shape right. There's still some, you might not be able to see it since I chose a very unfortunate color here, but the instrument, the data is on the higher side here, and we're still underestimating this a little bit. So there's a lot of specifics in terms of the cloud parameters that we need to start figuring out. Are we looking at our surface emission? How much of the emission comes from the atmosphere? Are we doing the simulation of the cloud right? Is the particle size correct? Are essentially the MERA database, the atmospheric database, does it see the same things as what the retrieved values from the observatory get back? So that's our work in progress now, and then in the future we're hoping to also look at the atmosphere and occultation. I see we're running out of time here, but this is my last slide. So yeah, so what I wanted to show is we produced images of the Earth. The idea here was really to demonstrate that we can simulate a planet with its full 3D surface and atmospheric variation. And we see that there's a strong difference in the integration times you get to detect different molecules as a function of what the atmosphere and the surface look like. And then finally, I was thinking about this, how do you apply this to James Webb, right? Well, I think it would be super interesting to really try and do the same thing for the TRAPPIST planets, because the TRAPPIST planets are, are very interesting object of study, but currently, if we apply the 1D models, we're going to be pretty far off, I would say, when we're trying to study these planets, especially since they're tidally locked. There's a massive difference between the front side and the back side of the planet. The atmospheres are anything but essentially 1D, right? So yeah, well, I think I'll leave it at that and take any questions if we have time. Okay, that's fine.
So the last talk of this session will be given by Rafael Luque, and he will be talking about Complejo Astronomical Los Colorados, an outreach oasis in the Andalusian desert.
So thank you very much for sticking till the end. My name is Rafael Luque. I'm a NASA Sagan Fellow at the University of Chicago, but today I'm not going to talk about my research. If you want to know about some exoplanet research, some Neptunes that I do, I'll be happy to do so afterwards. But this is work that has been taking much longer, that I've been doing for a much longer time. And that will be very humbling after the invited speaker has shown us how this type of work can lead to the space agency creation in a country. Certainly what we didn't lead to the creation of the Spanish space agency, but we did what we could. So this is the location that we work on. This is Gorafe. This is a small village in the south of Spain. This is situated in a place that is called Los Colorados. That's why the name of the place. This is southern Spain, very close to Granada. Here you have Malaga, which is a very nice airport that you can go, fly to, and then get to here. You can obviously go to Madrid and other places. This is the location that we work on. This is a very small village, about 200 people, and it is in an area that has been now declared UNESCO Global Geopark. So why was that? This was because El Geoparque de Granada, it was an UNESCO Global Geopark. This is not only because of the geological formations that you can see. This is very similar to what Grand Canyon is in the United States in a smaller scale, but also because there in Europe, it is the biggest amount of concentration of dolmens, megalithic remains in the whole continental Europe. So there are many of these fortifications, dolmens, that were used for burials in the Paleolithic times and Neolithic times. So that has been part of integral part of declaring this area, all this area that spans several municipalities as global geopark, but the sky has been also one very important contribution to this. So this is the sky that you can get from this area. This is one of the darkest locations in continental Europe. We have darker skies, obviously, in the Canary Islands, where we have observatories, but this is very, very similar to the darkness that we can get in Calar Alto Observatory, which is one of the largest observatories in continental Europe. This is very close to this location. This is a picture that one of my partners took, and this area is full of this type of trees. So this is work that I've been doing with others for more than a decade. This is me very young with more hair and less weight in these parts. We did some, this is one of the first activities that we ever did there. It is, I think, about 15 years ago. And we have been doing for more than a decade, we've been doing open public observations. We have been doing astronomy courses. We have been doing consultancy for government in this area, how to do the proper lighting of these things. We have been getting certificates for locations, specific locations that have very dark skies, so they can have some protection about what they do, and in order to protect and get some finance to maintain the lighting in the correct position. And we have been doing a lot of training for the people that live in those areas, very rural areas in Spain, to bring some sustainable tourism, something that can help their economy in an aging population. So this was work that we've been doing for many years, and we always dreamt not for going from village to village, but has a place, a center of operations for our work. And this is how Turismo Astronomico was formed, and it was formed with a dream. This is it's an NGO, it's a non-profit that does astrotourism mostly, but we always wanted to have our own place where we can do our outreach. So this is the team. Here it is. I am part of the team, obviously. I'm giving the talk representing, but these are the people that are mostly working on everything, especially on site. He is Miguel Pugnaire. He's an actual medical doctor in a very close village there. He's more in charge of the science and the outreach department. Miguel Hill, my partner since the very beginning, we both created this endeavor more than 10 years ago. He's in charge, he's a photographer, and he's more in charge with the projects and the management, all the communication, talking with all the mayors and city halls. And we have also joining very recently Deborah Smith and Eric Smith. They are people that live in the and that work with us with the settlement of the telescope. So this is the team that has been able to create an observatory just dedicated to outreach. This is how we envision. Sorry, I'm going back. Yes. No. So this was the idea. The idea that we had, it was to build something like a Mars colony or something where we could unite a sky and the land that we were sitting on in a very dark location. We wanted to have a place where we can do our activities. We had this idea of having kind of an amphitheater on the Roman style and some kind of domes and stuff that we could do it. And this, from being a project, a fantasy that we had, we have been able to build it. So this is how it looks a few years ago when the construction was officially finished. You'll see here 2 domes. We have this theater here and 4 other domes. So you see that it resembles the Orion constellation. That was one of the requirements from Miguel. He wanted to look like Orion constellation. And this is how it is called. This is Complejo Astronómico Los Colorados. You can have here the information. You'll see the activities that we do. You can get a newsletter. You can get everything that we do. This is the website. It is in Spanish and in English. The English part is not as complete as the Spanish one, but it exists. And if you need more information, just please write us and we'll be able to provide it. So this observatory is just mostly dedicated to outreach, but in the here, this is how it looks like. This is our control room. Here is where we have also a museum. We have the telescopes stored, the ones that we use here outside for public observations. We have here, these are the toilets. It's very important when you are in the middle of nowhere. Here we are working with solar panels, and we have this amphitheater that fits around 50 to 60 people sitting down. In this area, normally we put the visual telescopes outside to do our activities, the outreach one. We have a space here for more things. And here we have these 4 domes that at the beginning were empty. Now they have telescopes inside. And because they have telescopes inside, now we are not only doing outreach with them, we are starting to do a little bit of science. So I'm going to show you what are the facilities, because my main goal of being here is just to tell you that this exists and that we are happy to contribute. And if you can make use of these telescopes, please let us know, because we do a lot of activities, especially on the weekends, especially on the summer, but over the winter and during the weekdays, those telescopes are not observing anything, right? So there is a lot of time and a lot of dark nights and good weather nights in the south of Spain that you may use for your science or for your entertainment or for your education. So these are some of the facilities that we have. These visual telescopes, you may be not that interested on it unless you want to visit in person. We have also like kind of a science library here. We have some solar telescopes and visual telescopes for the night, but the main point are the ones in the domes. So I'm going to show you directly for the sake of time. This is the dome one that we have. This is a 2-meter diameter dome. We have this telescope, a Skywatcher Sprit. This is mostly done for wide field deep space imaging. So it's like kind of a big field of view type of camera. We mostly use it for astrophotography. This is an example of the field of view that this camera has. It fits the Orion Nebula kind of fully. This is one of the pictures that we have taken. This is Polaris. If you put a lot of hours on Polaris, you get a lot of this complex nebula around it. And this is a very beautiful image because this is what you get after, I think it was about 15 hours of integration. And this is what we needed to subtract in order to make this beautiful image. So I know we are here in the IAU, we are talking a lot about satellite constellation and protection of the dark sky. This is what we needed to remove as amateurs for a normal picture, okay? This is not the Rubin telescope or something like that with a field of view of several square degrees. This is just a very tiny field of view, and just a few hours of integrations create this amount of traces. So this is a true problem that we need to solve, and I'm happy to be here in a place where actually there is action being taken. So this is what we do with this telescope. We have another one, a Celestron C9, 9 inches. So I don't know the conversion right off the box, around 20 centimeters or something. We use this one mostly for asteroid occultations. As we have seen before, some examples of asteroid occultations. We also contributed to the Polymele asteroid occultation. We did it from several locations in Spain where it was also visible a few years ago. But I'm going to show you a different one, a more recent one that is from Betelgeuse. This is the field of view for this camera. It fills the Dumbbell Nebula very well. And this is a small movie of Leona, the asteroid Leona, passing in front of Betelgeuse. So you are now familiar with the type of data that you are going to see. So look at this star, the very bright one. And then it goes out. And it comes back, right? So this is the whole thing, a lot of preparation in the same way, several months, several telescopes, a lot of displacement. We went to many locations in Spain in order to track very well the size of the asteroid. These are from the telescopes that we had in Gorafe, but more of our telescopes were spread in other parts of Spain. This is from Betelgeuse, and that was our first astronomical official publication with the telescope that we have in Gorafe. This is a paper led by José Luis Ortiz, who is an expert in minor bodies and asteroid occultations. And here are my colleagues, Eric Smith and Miguel Gil, in a paper in Monthly Notices, which for them has been an extremely big deal and a source of pride. And I'm very happy for them because they've been in charge of everything, data reduction, all the stuff. I'm just supporting them, but not doing anything with the science they are doing. So this is very good. These are our first interactions with the pro-am community, trying to do some science apart from outreach. This is some of the results from the paper. Here you can see a lot of telescopes were doing this occultation of Leona, and that each location is tracing different parts of the asteroid, and that gives you very good constraints on the size and the shape, as Magan was explaining before. So you can stay tuned. There will be more telescope observations from our telescopes from Betelgeuse, a later occultation. And for this study, we contributed with these ones. We were in different locations. So the other dome has a C11, an 11 inches telescope. It is mostly used, we are doing now for exoplanets. Here are the properties, because I'll be happy to send you the slides so you know exactly what are the properties of these telescopes. We usually mostly now for exoplanet transits, and there is, we do a lot of other things, but mostly that, and this is the work of Deborah Smith. So this is more or less the field of view. It's a smaller field of view, a little bit deeper. And this is one of the first observations that we did. This is in February this year. It is TOI 2046b. Actually, this is one planet that I was part of the discovery team. And so we have reobserved it with our own telescopes, which is an amazing feeling. And this is the first one that we did in February. And since then, we have got plenty of them. We have been having more than 50 exoplanet observations since less than 6 months. I mean, Deborah is an amazing worker. She works extremely hard. And we have been covering and contributing to the Ariel ExoClock project, refining the ephemeris for the future target selection of the Ariel space mission from European Space Agency. So we have been doing this type of work, which is from the community, amateur community, but to help important space missions from the European Union. The other dome, Dome 4, 3 meters, is our bigger telescope, a C14, 35 centimeters. We also mostly use it for space photography, but this may be the most interesting telescope for you, for your research. If you need something that research requires something like this is our biggest telescope and more precise imaging. This is how it fits M81, the Bode galaxy. And here you can see some of the pictures that we've been taking in the last years. Beautiful. Eric Smith is a beautiful astrophotographer. He has done an amazing work. So this is what we do now on the program. I wanted to focus most a little bit on the program to reach this audience that may use of these telescopes, but we do a lot of service, a lot of outreach. This is our the thing that we mostly do. We've been helping in all sort of ways for the governments in the south of Spain and other different ways. We have been doing workshops. We have been doing all type of education and service. So we do these activities. I will let them here. This is one of the favorite activities for the kids, which is the water rocket launch. You see this one launching. The kids really love it. They make it and they do from scratch. And that's it. I'll just leave it here. This is the information, the email that will reach all of us, the website. I have my t-shirt here. I'll take my blazer out so you can see me with the website on the back. And if you have any questions or any ways that you want to contribute or make use of these telescopes, please let me know. You can reach me out in the Slack also. Thank you.
Oh, thank you very much, Rafael. Wonderful talk and nice project to see. So my question is just this, the telescope are like remote or like robotic? You can control them from everywhere, or you have to be there to observe, especially for like offering to people. And I know that I'm bothering people by this question that how we can like doing some online programs for African students to that maybe can use these telescopes to do some outreach and education activities.
Yes, great question. So the remote observing works, but it is not at a level of confidence that we are with a confidence level that we can make it absolutely open to everybody, because we still need to supervise. The biggest problem that we have now is the connection of our weather station with the closing of the domes. So the problem is if we leave it completely open to anybody and they are observing and suddenly there is bad weather and the weather automatic system doesn't close the domes, we are having a problem. So right now, the remote observations are possible. We are actually doing most of the observations that we have been showing all remote, but it is the work, especially in the winter, that we have more bad weather, to make everything so stable that we can offer it completely to the community, that we can open it. The ultimate goal of the observatory is to have it as a hosting place where people can bring their telescopes, their instrumentation, amateurs or professionals, and they can have a safe place where they can have their instrumentation access to a lot of nights. And for this, we need to be sure that the domotization, the weather station, and all the domes control, it is working good. But it is certainly possible now. It's on a case-by-case basis. We'll be happy to discuss any observations, but not yet open for everybody.
That concludes this session. So I believe there's a poster session going on in the exhibition hall. Please visit. Yeah, thanks to all the speakers and everyone participating.
You have us, no? Now we are the three of us. You also, so we are the session? Yes.
Hello, hello, hello.
And he's going to give, oh, there's a microphone. He's going to talk about the icy planets. Geronimo? See which one you want.
Yeah, we'll do this. Perfect, thank you. So hi, everybody. Thank you for being here. I know it's the last session of the day. But so today at the morning, I gave a plenary talk about, the new era for astronomy for James Webb. And this one is going to be shorter. So it's one more focused about astrobiology. So the idea I wanted to talk to you as more as colleagues to talk a little bit more about the spectroscopy that goes behind the search for life and how you define some of those metrics and some of the spectroscopic debates out there. And I tell you more about it. I thought it was a good opportunity to this smaller group to talk about it. Okay, so how do we test for habitability occurring in ancient Mars? And you all may have heard that different hypotheses on how we do that, but I think Mars is a good proxy to study, to explore the idea of habitability. So the trick that I've been using is isotopic ratios. And I wanted to tell you, I mean, I know it's a graphical animation of the process, but actually kind of captures the idea of a planet like Mars. So Mars is a planet that is smaller than our own. It's definitely, the gravity is less, but it's a temperate planet. It means that the competition between what we call thermal gene escape and the gravity is not retaining the molecules. So the escape of molecules from a planet like Mars is easier than in the case of our own planet. So if you keep that process, just by thermal gene escape, this is a simulation of the two isotopes of hydrogen. In this case, you see water has, one of them is deuterium, and the red ones are the hydrogen. So once the water molecule breaks down into the components, the hydrogen molecule, which is the life form, will, in this case, will easily escape because it has half the mass of the deuterium, which is much heavier. And it's a simplified process that the deuterium will be more protected by escape, simply by gravity than the lighter form. If you compound that with solar wind loss, and then you're going to have a preferential loss of the lighter isotope. So the Ryan hypothesis you can use in a planet like Mars, especially for an isotopy like D/H, is that if you had a primordial reservoir, imagine that we think that comets or main belt comets or small bodies were the one to deliver the primordial water to our inner solar system. Let's say they gave the same water to our planet, to Mars. So we can assume, for the sake of the discussion, that the primordial reservoir of water on Mars is the same as our own oceans, isotopic ratio, we can say. And in the atmosphere is heavily enriched. So imagine that by some reason there is a bend or connection between the subsurface and the atmosphere, then you should see a different isotopic ratio. So for many years, I was observing Mars, and I was looking for these peculiar isotopic signatures, not only to study the loss of water over time, but to study to see if there were specific loss of the plumes. But I wanted to highlight one thing about the D/H. You say, why don't you study carbon-14? Why don't you do oxygen? Why don't you do other isotopes? And the main difference is that the difference in mass between carbon-12 and carbon-14 is much smaller. Of course, 13 and 12, 17 and 18, or 16 oxygen. So then you have the definition, the difference in the masses are much smaller. That contrast between the escape is much subtle. In the case of hydrogen, it's a factor of 2 in mass. So it's a massive difference, and you can easily detect that. So, and this is, I didn't show that today, for example, to see, this is what, we do as astronomers, and this is using the BLT to measure these isotopes. And here, the green to the upper left, this is a CO2 on Mars, and upper right, that is, you can see all those blue lines, that is heavy water, well, it's not, deteriorated water on Mars. And I wanted to highlight how strong those lines are. These are huge. Actually, the isotopic lines of water on Mars are brighter than the telluric lines. And you think, how is that even possible? Well, we are in this case, we are in Atacama Desert, one of the driest place on Earth. And you have a low column, but nevertheless, the column there is a factor of 10 or maybe 100, depending on what, and that is a factor of, let's say, 60 relative to the place we're looking on Mars. But because it's so dry there, the water lines are so small and the Martian lines are huge. Here and below, you can see in the regular water. So in one snapshot with this instrument, with BLT, we could do the 2 isotopes and make maps. You're thinking, but this has to be, this is a paper that we did in 2015. You're thinking that it has been done before, and it was not. So the first thing we did this map here, and this is in the case, this is just the upper part. Here you can see longitude and latitude. This will be like a full map of Mars. We did this map, and I wanted to show the scale here. This is 1 to 10 times terrestrial. So in here, the bluish color will be 1 ocean value isotopic ratio. 10, which is the red one, is 10 times terrestrial. And I was shocked. I mean, I was not expecting the isotopic ratio to change so dramatically across the planet. So if we are thinking that this is a chronometer of water loss, it should be the same everywhere. If it's changing across a volcano or something, then it's no longer a chronometer. The chronometer is broken. So we were scared, and actually I was very scared when I saw this plot first, and I spent, not 8 months getting educated myself on why this thing, and I thought the data was bad or anything. I was almost giving up. And then I got educated that terrestrial people study our planet, they use the isotopic ratio to infer the formation of clouds, because the fractionation of the CO2, the water clouds, the two isotopes will behave different and condense at different temperatures. So those things you see, these are clouds on Mars. But the key thing that we're seeing, we're seeing the snowing and in the winter hemisphere. But the main message that we were getting from this is we can separate climatology from evolution. The chronometer could be separated from the local phenomena. And the main driver of this is we can now, before people were making the average of all that. Now we realize you cannot make the average because, of course, you will make the wrong chronometer. But now you can understand that the true value is the one when the two isotopes are fully vaporized, and it's around the greenish color there. One thing that made us happy is that the Curiosity rover was making measurements around Gale Crater in there, and they were making exactly the same measurement that we were doing at the D over H. So that for us, we felt a little bit confident that the number we were getting from afar made sense. And I have to say, this is actually pretty cool. So look at the dates. So this measurement here was done in Keck. So I was at Keck observing that night, the 24th. We finished observing that night. And then I flew to California to Santiago to Paranal, and I came to VLT that night, and I started observing on the 29th. Because there are different longitudes between the two observatories, you can actually map a different area of the planet almost at the same time. And when the cool thing is when you map them, when you map them, you can see that these things are real. This is really climatology taking place on Mars. You can actually even use 2 telescopes, complete different spectrometers. So these signatures are definitely real, and it was very, very interesting thing. You can use this chronometer from afar to make these measurements. So you're saying, okay, great, you measured the average of Mars. What is the significance of this? So I want to go quick here, but normally, what you do is you do like this here. We have time. This will be present here, 0. 445, let's say, formation of the solar system. And I'm going to put here the D over H relative to Earth. So the value on the atmosphere, let's say, is 7. And I make this transformation from the gas phase to the ice phase, just simple transformation. It gets fractionated a little bit when you make it an ice. So the true value in the polar caps, we can infer that is not the full polar cap, but the upper layer of the polar cap that is fully every summer gets vaporized and they release all that water. That value is around 8. So what do you do with that number? Well, we are very lucky that we have a meteorite that we by the composition, by the way that the meteorite is, we know that this is a meteorite from Mars, which is 4.5 billion years old. And I think it's fascinating about this meteorite is they measure the D over H, and the D over H is 1 times terrestrial. There is a spread on the numbers, but a key thing is that the meteorite, which is very old from Mars, had the same isotope as our own oceans, which I think for that's pretty interesting. But the key thing is that we also got measurements of Curiosity here. This is on C2. So the Curiosity rover made a measurement close to the surface, and they also measured the isotopic ratio. You see how the isotopic ratio is going up all the time. And this is just the escape process I was telling you. It's happening at a high pace. Then you can connect by a simple model. And then I just changed. So I'm going to go back just to show. Look at the y-axis on the left. I'm going to change it now. You can do a very simple transformation. It requires some modeling, so this is model dependent. But you can transform from the red trace into the blue trace using an equation. And that tells you how much water was in the past relative to the present. And interestingly, that equation is based on, I was telling you about the mass escape rates and those things. It's simplified, but it's powerful because it tells you that, you know, if you know the value today amount of water, you can know how much it was in the past. And we can say that at least Mars lost 87% of the water that we can measure today. And this is the water that's been lost, that you know, it's been interacting and it's going through that process of loss. So if you have any water lock under the surface, that will not go through that process. So that I would call this a lower estimate how much water was in the past. So what do you do with that? So what I did is it's a simple simulation too. I just took the polar caps. We know how all the water in Mars is in the polar caps, multiply it by 6.5, and then let it rain on the planet. And because of topographically speaking, the northern is lower topography, the water will tend to accumulate. And this is just a topographical, just put water, multiply. I mean, this is nothing more than that. But incredibly, when you do that, you start creating these shorelines that actually match the geology that people are measuring today. So we are measuring something from Paranal in Chile today, and it's telling you about 4.5 that matches geology on the surface. That was really, really interesting. And it confirms this idea that Mars had a big body of water. The big debate still in Mars. Mars is still very far away. So we don't know for how long this ocean was liquid. So there is the hypothesis that I would say the most favorable hypothesis today is that Mars had a big body of water, but it was transient. It was times when it was there, then it was freezing out, and it was when there was a hit of a meteorite or something that was happening. Big geology, explosive geology will produce a enhanced greenhouse. It will warm up and release that. So we think that this ocean was actively intermittent. It's consistent with the hydrological cycle that we see on Mars. So are there signs of recent geology or biology on Mars? And this is the main thing. And I told you, and I wouldn't go so deep here, but I was telling you today about how can you measure biology? And somebody asked a good question today about how do you know it's life just by looking at a single molecule? You cannot. So the main driver I wanted to show with this slide is that to show that in the case of methane, which is a powerful, being called a very powerful biomarker, it can be produced by a lot of stuff. Geology in this case, you can get delivered by a comet, or the more interesting prospect of have life. In all the cases, the perspective of having methane on Mars implicates some sort of change on the planet. That's why people have been searching for that for so long. So methane, we can call an activity marker. Otherwise, if we get photolized, it will last 300 years. So this marker telling you that something happened within 300 years. So if you go back to this hypothesis, you may have a reservoir here, maybe geology is happening on the planet. And then occasionally you get this release of methane. That was, again, we are testing this hypothesis together with isotopic ratio. And this is what as astronomers, we were trying to see if we can do that. So when I came to Goddard, actually I was a student in Germany, and Mike Muma, who is the person who led this effort, he already took the data from this telescope 2 years before I finished my PhD. But he called me to Goddard to work on the data analysis on this data, which is extremely complicated. And why is so complicated? So this is a ground-based measurements of water and methane on Mars. And the main thing that it was in the data, and it's still in the data, is there was a signature, okay, water was known, this is not nothing extraordinary, but the methane signature was localized in specific areas. And I arrived in 2005 on Goddard. We spent 4 years full-time working on that, and the signature was still there. But it's extremely difficult signature because you're looking for methane at very trace amounts, very weak signal, at a Doppler signature line embedded in a massive atmosphere, which is our own atmosphere, full packed with methane, and not only methane, but the isotopic lines. And unfortunately, the line of methane that we were looking on Mars is really very close to an isotopic line of carbon-13 of telluric methane. And because of that, these measurements have been controversial, remain controversial, and I spent 3 years after making these measurements, and I could not see methane with any other observatory. So I'll leave it to your inference of the significance of the measurement. Could be a sporadic process, but as we know in science, those are rare to explain. But the thing that was happening on Mars is that on the surface of Mars, we have a rover, and the rover occasionally see also plumes of methane. So that also added to the debate. So we actually sent a spacecraft to Mars to try to solve this debate out. And it was actually ESA selected this, driven for some of this stuff. So we make this paper in 2020 with Elise Knudsen, a student working with us at Goddard, and we have this spacecraft. And I know this is a busy plot, but this is, in this case, latitude on Mars, and this is altitude. So we have this instrument that make occultation measurements across the planet, and all these numbers here are upper limits. So the red is more sensitive you are, but there are never detections. We have searched for this molecule with TGO for 6 years, at every altitude, at every location, we still don't see it. But not only we don't see it, the upper limits are factor of 100 to 1,000 lower than the previous detections. So again, big debate. But you can notably see that there is a gap here. Just mark on what the Curiosity rover is. So there is a whole army of modelers right now that they're trying to infer that there is some plume ejection that it may get hidden just below the measurements and all that. As you can, again, it's an inference, but it's a big body of research. So the problem is that when you see a problem like this, you realize that it requires a new way to see the data, because if we keep doing this, we're gonna never solve the problem. And I think that's why James Webb is good, because James Webb is in the top of the atmosphere. We don't have the telluric problem, and we can measure the whole column all the way to the surface. Maybe we miss a little bit the bottom because of the aerosols if they are very thick, but typically we can see all the way to the surface, and we don't have the telluric problem. So one of the aspects we wanted to do with Mars to see we can detect this signature with James Webb. So this is the spectrum that we took from James Webb. And you're saying, why you cannot do it from orbiters today? Well, the instruments don't have the spectral resolution to distinguish this very weak line. I will show you a simulation, what you expect the simulation. But this is James Webb. In the near infrared, you can see we have these are known features of Mars: CO, water, and CO2. This is all great. But you can see this is on top, we have a model. So we can pretty much, with classic acclimatology Mars, can play most of the morphology of the spectrum. So big the effort has been, and this is a press release, so on purpose, this is a smooth spectrum. So we didn't want people to, digitize, try to pull out a methane signature here without, doing a careful thing. So we are looking at a signature around here. So we have the data are actually public. You can all go and look at the data. Extremely tough data. The problem is that, just to give you a sense how difficult it is, and this is what I think is gonna be a limit of the James Webb data. The maximum resolving power of James Webb is 3,000. The resolution that we use on Earth was 30,000, 10 times higher, and these lines are very, very narrow. So this is the signature we expect for methane if it's 50 ppb. The signature that upper limits that we get from the TGO orbiter is 50 parts per trillion. So it's one factor of 1,000 smaller than this. So this is already tough, and you can see there's a massive solar feature. So if you want to divide this, by 1,000, you see how difficult it gets to go that sensitive. But the Curiosity rover is making measurements, or there was a few papers about it, that the rover is seeing plumes of 10 ppb. So we should be able to test those with James Webb, and that's something that we're actively working on. So this is the preliminary, and I'm gonna just to summarize quickly. We only got 15 seconds of James Webb, and we're still working on the data, but just to give you a flavor, this was test data, just like demonstration, does it work or not? 15 seconds on Mars, and we got this SNR of, incredible pixel by pixel of almost 10,000. The photon counts are extraordinary. We are actually limited always by the detector only. We have not seen methane, and we are looking at the upper limits, but the main thing is that, this is what I wanted to say here, that we have an upper limit within 1 or 3 ppb. Again, remember, the plumes that I showed you about from the ground base, those were 50 ppb. So we are already more sensitive than the previous claims. So pretty much those can be ruled out at the time we observe. But we want to go, because the Curiosity rover always been making a measurement, which is the one we want to test. They claim that they always see a background level of methane, like always a constant value of methane. And that one is around 0.5 ppb. So we want to penetrate that upper limit to see if we can test that. And that's the main driver. But you can see what we are not there. We are missing a little bit. And if we get a factor of 10, that's what we want to get. We may get to break that limit. That's why we are actively working. It has been a tough job, but I wanted to give an update on that. Again, I think James Webb is great, but it doesn't have the resolving power, if you ask me, to do this more sensitive as we would like to do. So I want to talk about this quickly. You probably heard about phosphine, and you see how complicated it is to define a biomarker. Phosphine is an interesting molecule because it should not be there. And it's like, we're always looking as an astronomer, molecules should not be there. They're proxy for activity. So a few years ago, So the main idea was that a molecule like phosphine, because it's a very rare molecule, should indicate perhaps biological activity. So searches with JCMT and ALMA claim a detection of 3 sigma of phosphine. Several teams look at the data, they didn't see it. We work a lot on that. We actually reanalyzed the data independently, and we couldn't reproduce the detections. And it became a very contentious process, as unfortunately of science. But I wanted to show you a little bit about the challenges of the data. So the initial detection was like this. This is our analysis using our own routines. So we didn't see the signature from the phosphine. That was a surprise. So immediately we tried to contact the team, but they didn't reply. So we contact also the journal, and the journal said, well, you need to maybe write something to a notification to the journal. So before we do that, we embark other teams from the whole world. So we actually, people in Europe, people in the US, different teams analyze the data independently, and all of the teams, we had 4 pipelines. None of us saw the signature. So when we put a paper about that, they revisit the analysis, the original paper, and they did a new paper. Then they say, well, yeah, we did a mistake. And the signature, they say, we still have a detection there. And it was that. So in our paper, we demonstrate that that signature, that little wiggle that you still see there, is because they use a very special baseline in the analysis. The data is very tough. ALMA data has this big baseline. So if you add a first polynomial fit to this, you get this. So if you do the 6th order polynomial, it's pretty flat. By 11th, it's flat. But if you do 12th, you see something. And they pick 12. So, and it was, it's a skepticism about that. And I don't think they did it on purpose, or I don't think it was intentional. But I think when you do this very, very long baseline analysis, you need to watch the possible systematics. And I think that's one of the challenges with such a data set, when you are playing with such very complicated baselines of this. So we got a paper about it and say, okay, we need a new measurement to this. So we embark. So in this paper, we report that there is no phosphine on that data. But we also went and took new data with Sophia. Made the data available immediately, and we also didn't see it. And there are papers, and there is also big back and forth papers about this, but unfortunately, we don't see the signature. Okay, now I'm going to switch to more positive things about Europa. And how do you test, going out? This is a great team again. I want to highlight all these people, and sincerely, they have really contributed to this project. I mean, for example, in the audience here, we have Sarah Faji and Vincent Kaufman. Stephanie has been the architect of all this project. Hattie has been fundamental to, she gave us the time. She invited us to the project. And Kevin, for example, at JPL, he did a lot of the modeling of the lab to interpret all the data. And Lucas, also in the audience, he did the precursor searches of the plumes, and they were fundamental for the searches of plumes on Europa. So what is an ocean war? I talked a little bit today. We have a cross of ice, it's an ocean, and we are looking for the connection. We're looking for the connection because it's a way to provide a window to what happens in the ocean world. So compared to the plenary, I want to tell you more about the data. So I showed you today about that we saw this localized Tara region. This is an image taken with James Webb. We saw this very localized anomaly in color. But the main thing we saw is this, and I didn't show it today, but this is what I show. It's the beauty of James Webb. For every single pixel, we have a spectrum. And you can see we got this double peak of CO2. Never seen before the shape, and that was a surprise. So we had to go to the literature. We actually find an ISM paper that the actual lab studied trying to interpret ISM data, interstellar medium data. And they used some mixtures of different ices. And we discovered that this could be a mixture of CO2. In this case, it was methanol, but we don't think it's methanol. We think it's that it's just CO2 in a specific matrix that makes this very complicated shape. And then we map it. So we divided this signature into 2 peaks, the 4.27, 4.25, and then we also had another signature. We had 3 detections of the CO2 feature. And the great thing about it, not only the detection of CO2, which I think is cool, but it was that it was localized, only in this area. And being localized, that gave us the indication that this was an active source of the molecule on the surface. And that provided a carbon source and added to the prospects of being an interesting place habitably. So I think that was the key thing about these measurements. And lastly, I want to talk about Enceladus. I just show you today about, in the plenary about Enceladus and again, as an ocean world, but I will show you a little bit more about the data, how the data looks like. And I wanted to show you a few things about James Webb and the power of this observatory. And again, this is the power of a general observatory for astronomy. You say, hey guys, I'm in the planetary division. I have all the rovers and all the missions I can send, but I'm an astronomer by nature, and you need observatories like this. They are foundational for the science we do. And this telescope went to observe Enceladus. It did 268 seconds on Enceladus, which is nothing. And it transformed this spectrum never seen before of Enceladus. Look at the SNR, look at the signal to noise ratios. Some of these things are even in the calibration pipeline, but it's so pristine. These are orders of magnitude sensitivity in a small little moon so far away. This is extraordinary. And the key thing is that, first of all, while we see these beautiful signatures of water ice on the surface of Enceladus, we knew about it, but that was cool. I mean, I've had to say, somebody else is working on that. It's just beyond I don't know how to even model that. It's so complicated. But the main thing is that we didn't see these ices here, neither emissions from these molecules. But we did see a little bit about here, like an emission. So I'm just gonna finalize. I wanted to show the spectrum. These are the little, these real emissions. These are emissions from the plume of Enceladus, and we can map it pixel by pixel. Enceladus is a single pixel, and the plume was, much bigger. Actually, it went beyond the instrument. We can, it could be measuring. James Webb is so sensitive that we can actually map the plume all the way away. And this is something extraordinary. Again, we're talking about 4 minutes of integration, and you can do all this stuff. And I want to finalize with this animation of the torus, the donut that I was showing you today, and we can actually measure the density of the donut. We can measure the amount of water in the plume, the production rate. By combining those measurements, we can make that measurement that is going to help us as we now actually work on maybe the design of an orbiter and lander to Enceladus. These measurements with the General Observatory are transformational. So I think as an astronomer, planetary scientist, the value of an astrophysical asset like this is key for us. So this is, and I'm gonna just leave it there. Search for Life is just starting. Thank you.
We will have a little bit of time for questions. Is there anybody who would take the opportunity to ask a question to Geronimo? Do you have a microphone somewhere? Yeah.
Going to the last
Yes.
picture of Enceladus, this cone of material, it's an indication that the material is coming just from one region, or it's more spread around all the surface of Enceladus?
Yeah, that's a great point, Gonzalo. And I'd say the key thing about these measurements is that we were lucky that we had Cassini. So we had isolated measurements of the plume, but we didn't see it in a full extension like this. So this simulate, actually this is the model here. The model that we did, it was a single jet. We can actually get the cone, the shape, we can actually collimate it. So we identified how big the cone and the production rate and the velocity. So it's a single area, and it's actually known on the surface of Enceladus. It's called the tiger stripes. So, and the key thing about the measurement is the shape, as you say, but also the production rate, which is the number of molecules per second. And that number, it was very similar to what Cassini measured 10 years ago. So, I mean, by having James Webb, we can keep looking at the plume. But, we are taking data, we are hoping to take data with James Webb again, but for much longer time now. But we're gonna look for the other molecules, especially we didn't detect CO2, neither methane, neither CO, but we know they should be there. So we need higher integration times. That's why we asked for time. They gave us the time to go deeper, and this is the main objective of the next search for Enceladus.
Evine van Nishoek, Leiden. You just answered my second question, which was whether there was any sign of the gas phase CO2 molecules yet, because it would be surprising not to see that.
Yes, and you're perfectly right. So especially with the sensitivity of James Webb, we were hoping to see it, and well, you can see there the spectrum. It's much noisier, I mean, and continuum-wise, but sensitivity-wise, it should be there. And I have to say, for methane, compared to the Cassini measurements of the flyby, we were very close to the detecting. So if the composition remains, we should be able to.
Right. So this brings me to my first question, which goes back to what was also asked this morning about MIRI, about the mid-infrared. Mars, the CH4 band at 7.6 microns, has that been looked for already, or?
No, that's a great point, Evin. So the problem with Mars, we cannot do mirroring. It saturates. Actually, pretty much, the problem with Mars is James Webb doesn't have a neutral density filter, but it's bad for people that study Mars. So we cannot do mirroring. We cannot do even IFU. We can only do slit spectroscopy with NIRSPEC at specific wavelengths because it saturates almost
even the MRS is saturated.
Yeah, everything.
Okay, and for Enceladus, because when we look at our protostars, we see the CO2 bending mode gas phase much more readily than the 4.7 micron stretching bands, which of course needs more energy and has a very high Einstein A coefficient to expand.
So you're right. So we look at the mirror data, we didn't see any notable signature of gas phase on the mirror data. There is a band of water, of course, at 6.7, but we didn't see it. And we look for methane there, we didn't see it. And we also look for ices of methane, and also there are bands of there, and even there methane, but we didn't see it either there. It's not a surprising thing, though. One of the things that about the measurement that we want to change now is that, as Gonzalo was asking about this single source, so the southern pole is pointing behind us, so we don't actually see in the simulation the source. We don't see it; it's hidden behind the hemisphere. So if that place is releasing material ices and being coalesced near tiger stripes, we couldn't see them because we are not doing. Now we are looking at a different side of the orbit, so we're going to be looking at the tiger stripes from the front. So we hope that we may be able to see some of the ices accumulated nearby the area. Yeah.
Okay, thank you.
Let's thank the speaker again. So next up, we have Sarah Fauji, also from NASA Goddard, and she's going to talk about James Webb observations of 29P.
Waiting for the slides. Well, thank you for having me today, first of all. And we're gonna talk about a center, 29P, Schwarzmann-Wachmann 1, which we're gonna just call 29P for the time being. Here we go. Okay. So I just want to start saying that this was a very great team effort. And then I'm going to present today the observation of this object with James Webb. And I'm going to focus exactly on the CO and the CO2 emissions. So just first of all, what is a centaur? Because not everybody does small bodies. So a centaur is a small body like a comet originating from the Kuiper belt. So basically it's a trans-Neptunian object beyond Neptune that has an orbital that is transient. So it's moving towards the giant planet, and it stays there for some time in this gateway, and then eventually becoming a short period comet or a Jupiter family comet, because they are interacting with Jupiter. So as you can understand then, being such a transient population of small bodies, they're very interesting because they can provide key information between the heritage composition of small bodies from the TNOs, for example, to versus the evolutionary signature in comets. So in short period comets, for example, that has been very cooked by the multiple passages around the sun. So not having experienced that such processing, centaurs are key to disentangle between these two signatures. And 29P, of course, is one of the most active centaurs, if not the most active centaurs. And this object exhibits major outbursts, which are not really periodic, like they are periodic, but they just happen, and it doesn't depend on the heliocentric distance or the perihelion distance. It's something that we still hasn't understand as scientists. And so the CO outbursts that we've been detecting over decades are sometimes correlated with the dust, but not all the time. So this still is something that it's quite interesting about this object that we don't know, we don't understand. And of course, when we talk about small objects, and comets and asteroids, the relevance of studying this object is because they are the remnants of our planet formation. So we want to do taxonomical studies and isotopic study to get key information and understanding of the history and the origin of our solar system in the first place. And so based on the regular time, GEO time, cycle 1 observation, the program is Adam McKay PI 2416. We observed 29P the last February on 2023. And we got just very few minutes of exposure time, like 5 minutes. And we got near-spec data in the prism mode, covering from around 1 to 5 micron with the resolving power about 300. And as you can see here, I'm showing the orbital, of that day, and just an example of a slice of the IFU, just to show you where the target is and what is the thing? Oh, this one. Yeah, but the target is, so 29P here. I think this is around 1.6 micron, so reflected sunlight. And just keep in mind that the nucleus here is 60 kilometers, and each pixel of the IFU, it's 0.1 arc second, so it's about at that distance 390 kilometers. So the nucleus of the comet is inside the center pixel. So what you're seeing here is probably reflected sunlight from the dusty, icy granule around it. And so what we did, of course, is trying to extract the spectra. So we just put together first 9 pixels from the center, and here's an extracted spectrum from a box of 0.9 arc second. And clearly, the first thing that we all saw was these two beasts, the CO and the CO2 emission. And CO2 was the first, not really the first detection, but definitive detection. There were upper limits before. So we confirmed the CO2 presence, and we saw the isotopes of CO and the CO2. So it was incredible. The signal to noise, as Geronimo mentioned, is being incredible with near spec. So you can see here, I'm plotting here wavelength, of course, and spectral irradiance in Jansky. And you can see actually here from the high signal to noise, the organic feature that, some other people in the team are working on it. Of course, the water ice, perhaps, 3 micron bands, we still clearly don't know. We need modeling to identify that. And probably, perhaps, a tiny bump over there, 2.7 micron, which could be attributed to water emission, but still don't know. We have to model out that part. So I'm going to concentrate for today and this part of the talk about the CO and the CO2 gas emission that we just published last month in Nature Astronomy. So again, CO and CO2, what we did is try to model these features, try to identify all the isotope. And you can see here a zoom of the identified isotope, and you see the Ni1 band of the 13 CO2 and all the other band of the 13 CO, CO17, the C17O and the C18O. However, a big problem for this first analysis was opacity, because as we well know, 29P has a lot of CO. And so both CO and CO2 resulted to be optically thick to a first analysis. So we decided to embark in a pixel by pixel retrieval, which was necessary to study the right amount of molecule that you had sampled in your single pixel. So what we did, we first did the first analysis on the 9 pixel to get the flavor also of the rotational temperature. We confirmed to be a value that was consistent with previous measurements. And then we performed this pixel by pixel retrieval. And we could, in that way, study the anisotropic morphology of the outgassing. And so what we did here was the isotopic ratio were kept fixed at telluric value for the time being for this retrieval. And then we did a multi-band, a multi-isotope retrieval, correcting for the opacity at the pumping level of the fluorescence. And so this was all included in the PSG, the planetary spectrum generator, radiative transfer. And when we got the results of the pixel by pixel retrieval, we were very shocked. I could not believe I started with 3 pixels and then 5 by 5 and then 10 by 10, and then I went 20 by 20, and I could not believe what I was seeing. We saw basically a single jet of CO towards the north pole, the north direction, and then we saw 2 jet of CO2 swiping in the opposite direction, one towards the north part and one towards the south part. And these here are the data. So I'm reporting the column density multiplied by the nucleocentric distance. So it would be basically the column density divided by 1/ρ to see the anamorphicity of the outgassing. And so to characterize this, what we did is a 3D model of jet outgassing. Basically, just inputting the production, the reduction rate, so molecule per second, yes, the velocity, the expansion velocity, and the aperture of the cone, we could model basically the data, the 2D data, because we were doing this 3D model of number of molecule per pixel, and then you were summing over one dimension, you were getting, the molecular density, the column density. And so we could see that we had two, clearly, jets for CO2, and one single jet for CO, but also a frontal jet towards us, which was confirming what was seen in decades of observation of radio astronomy, whereas the CO was always observed these jets towards the observer. And so this huge dichotomy, because again, the nucleus is within the center pixel. So we're seeing a huge extension of gas coming from just something that is inside the center pixel, right? And so this huge dichotomy between the north part, the north part here and the south part here, where you can have one side with a lot of CO and CO2 and one side that is poor in CO. Let us think about the nature of an object that has such, strong emission, outgassing. And so if the outgassing are related to the nucleus information, how the ices are stored on the nucleus, we can think that perhaps a possible explanation could be the following. So what's the story behind this? So when we look at short period comets, which are the end of the evolution of these centers, right? The orbital evolution, the 70% has been observed by spacecraft are bilobed shape. And here, just an example, even AP-Tuttle with radar observation was bilobe. And then we have an example from the New Horizon mission that we know the Ultima Thule was a bilobe shape. So maybe binarity and bilobe shape is something that can be related to either evolution or formation. Clearly, we don't know that, but there are many different hypotheses of, for example, differentiation of some processing that can shape the nucleus or can shape the one side of the nucleus that not necessarily has to be bilobe, but it gets depleted in one molecule versus another one due to, for example, a very high obliquity of the object. But not having that information about 29P, let us have this interpretation towards the possible bilobe shape of the nucleus due to this very strong dichotomy between the north volatile side rich, where very, very high ratio between CO and CO2, about 300, and a very poor CO side where we only have CO2, and basically there was no ratio there. And this is consistent also with broad measurements that have been done before. And so what's the story behind this? How can we think about that we have these two bilobe that got together so different? Well, when you think about the protoplanetary disk, and we know that comets form within the giant planets region and within many distances across the protoplanetary disk. And so we know that snowline naturally are at different distances. Clearly, they are not fixed in time, they evolve, they move. We are not saying that they're static, of course. But what happened is that perhaps you can think about two different fragments that form into different regions and clearly experience different processing at different, chemistry there. And so you might have a very CO-rich fragment and a very CO-poor fragment, or a fragment where CO effectively transformed in CO2, while another one that didn't. So effectively, perhaps those two fragments got together, and we're seeing today this bilobe probably shaped nucleus with this strong dichotomy. So that is an example of our interpretation. To move forward the conclusion, I just want to also mention that we, as I said, identified the isotopes in this target. It was very, very challenging because we were working with the prism mode, so we didn't have a very high resolution. And also when you see here a model of the isotopes here, the main isotope and the isotope, the other isotope, you can see how, first of all, the bands overlap to each other. They clearly have different opacity, so it was very, very hard to, fully establish reasonable number. And so what we did was a statistical approach to this problem. So we fixed the value of the isotopic ratios to telluric, and then we perturb it to different, 10 times bigger and 10 times smaller. And we saw when we could have, with a statistical approach, a cumulative distribution function, basically, when we could have the value of an isotope, our isotopic ratio, and then we reported in the paper plus minus 1 sigma that value. So we saw that we were consistent with telluric within that sigma. And so going towards the end, we provided the first dynamic detection of CO2 and detection of the isotopic carbon and oxygen in a centaur. And we saw a very complex outgassing of these two molecules, indicating possibly the presence of two very different compositional lobes of the nucleus. You first assume that the gas count is informative of the ICs on the nucleus. And of course, we implemented this very important optically treatment of the fluorescence modeling for the planetary spectrum generator. So thank you, and exciting about centaurs and small body with James Webb.
Quick questions. Did you say anything about how long the exposures were, like in total?
I think we were around 5 minutes. I think I have in the first
Okay, but it was a very short observation.
Oh yeah,
so
very
is there
short.
a plan to do like a survey of all
Yes,
sectors?
I am gonna try to apply for time. I want to do NIRSPEC, high resolution. I want to do more observation. I want to do multiple, instrumentation too. I want to explore also the longer wavelength too. Yes, that's necessary. You need to see if those jets change or not. So this observation, it was part of a survey of multiple centers. So the team observed different objects. This time it would be beautiful to monitor 29p and so see things. It was great though, a few minutes of observation time were.
Yeah, beautiful, beautiful data, obviously. I don't know if I quite caught this. So is there a light curve available for this that shows any sort of shape, or is it,
There were some works on the light curve and shaping, and I was talking to Charles Chamambo, which is co-author of this, and he was like, oh, wow, I thought about was more spherical, right? But I knew that there are other teams working on new light curves that maybe also were not convinced about being spherical. It could be, elongated. So this also provides new information. I don't know about, a very high resolution light curve that can provide more information about it. It's faint, and with outbursts and everything, it's also not easy. But yeah, it's something to definitely put together because the bilobe shape is inferred by the gas, right? So the outgassing, but.
Right. Great, thanks.
Yeah, thank you.
So we got a question from online, which is more about logistics, is that they cannot see where we point. I don't know how to resolve that. So maybe describe a little where you're pointing at. There are limitations to what we can do with technology. Next speaker, Cyrielle Opiton, who from the University of Edinburgh, and she's going to talk about the relation between size and composition of comets.
Thanks, Dennis. Okay, so I'll tell you a little bit about a study that we've been doing. This was led by Jamie Robinson and Yuri Malamud, and hopefully I'll do justice to their work today. So it all started whenever we write a proposal about comet, we all, oh yeah, comets are some of the most pristine remnants of the early solar system. They were formed and they were stored in very cold reservoirs, and they've remained mostly unchanged. Whether that's totally true is another story. So comets can still get processed to some point, potentially, whether before going to their reservoir or potentially just after their formation. And so in a paper in 2002, Yuri Malamud and collaborators have shown that if you consider a comet made of a pebble structure, you can actually have very low thermal conductivity. And the consequence of that is that you can have more heating via radionuclide decay than was previously thought, which leads to sort of a gradient of temperature within the nucleus of a comet. And that's what the figure over there shows. It's a figure from their paper, which you have the time since the formation, the radius, and that's an idea of the temperature. inside the nucleus of a comet. And so if you have these heating, these gradients of temperature, eventually that might lead to sort of a differentiated onion-like layers in the nucleus of your comets, potentially due to trapping from some amorphous, preferential trapping of some molecules in the amorphous ices. And their conclusion is that if that kind of a model is true, you'd expect to see a correlation between the size of a comet and its composition, meaning that comets, the bigger comets would have more highly volatile material, more of the sort of very, very volatile ices like CO, for example. And we had a discussion at a workshop and I said, well, we actually, have we ever checked that's true? Have we ever looked at correlations between the sizes of the nucleus of a comet and their composition? And we couldn't find anything easily in the literature. And so we just went looking. And what we did is we did a very, we took data from a lot of literature sources. We did a massive literature search from both studies with a lot of comets, but also individual studies. We tried to gather everything in the most homogeneous and sensible way possible. It's very difficult because measurements are made at different wavelength, different instruments. And so it's something that's not straightforward and there are biases involved in that. We decided to consider the abundance relative to water in these objects. There are controversies whether abundance relative to water is what you should look for, but as you'll see later, the sample was a bit limited already. So, well, we do with what we get at the time. We figured out which, like the heliocentric distance range, or most of the time the median of the heliocentric distance range at which a comet was observed. Said when we tried to have the most homogeneous data set possible. So when we had the same measurement for two different comets, from two different sources for the same comet, we privileged data from big studies so that we have as much of the data points as possible coming from the same studies. And obviously preference with the measurements coming with so that's the first side for the composition, which I forgot to mention. We looked at both parent volatiles, so more complex volatiles, but also at daughter species, just to be inclusive of everything that we could find. We also compiled the sizes of the comets. And so composition is already not easy to combine everything in a single study, but when you go to size, it's even more complicated, just because particularly in the objective of this study, we wanted to compare to composition. And when usually the comets that are bright enough for you to measure the composition in detail means that there's a huge coma around it and you don't see the nucleus, which poses a problem to measure its size. So it was very, very tricky to find enough data to do the study. We privilege data for the sizes where you have a direct detection of the nucleus, or whether direct from a spacecraft, or at least, direct measurements of the nucleus sizes versus derived from the sublimation, for example, from how much water it can produce, and inferring then which surface it must have. We selected, when different measurements available, we selected a smaller size to be conservative, with more modern sources and with uncertainties. Again, there were a series of choices that had to be made over there, and I invite you to read the paper for more detail about all the choices that were made. And that's a plot here showing kind of the numbers of comets we have at different sizes. As you see, we don't have a lot of big comets observed. Again, these big comets are very active and it's hard to measure the nucleus. It's always the same thing. So we are really lacking the big comets. So coming on to the results now, we've been taking the intersection of the composition measurements on one side, the size measurements on the other side. We had over 1,000 unique measurements for 83 comets. That contains that 1,000 measurements is for all species. So you could actually, starting for a species, for the number of species for each comet wasn't that big. And the plots there on this figure it's a bit busy, but you can see it's a range of species. So you, for example, have methane over there, you have CO, it's over there, HCN over there. So it's all the species that we found for which we had more than 5 points. We didn't consider anything where we didn't have 5 points. And so it's the ratio, the abundance relative to water as a function of the nucleus in kilometer here. The points are color-coded depending on the heliocentric distance at which the comet was observed, which I'll come to later, which was turned out to be quite important. We also did differentiate between different types of comets, so comets coming from Oort cloud, comets coming from Kuiper belt, trying to see if there were any differences. We computed Pearson correlation coefficients, so looked for value for species with a high value of the correlation coefficient and a low p-value for significance. So when I'm talking about not significant slope, that's what I mean. It's statistically not significant. So if you have a first look at the data there, you see there isn't that much trend for most of the species. So if you look over here, nothing obvious. And if you look at most of those species, actually, you don't have that much point. So the fact that you don't have any trend, I think, doesn't mean in all the cases that trends are not there, but that we don't have the data available yet to look at it. But there are some species where we could actually see some significant trends. And it was the case of mostly CO, where it's very, very significant here. So you can see really a real correlation. The points line up quite nicely. We were not expected it to be that clear between the CO to H2O ratio and the radius of the comets. Seems that there's something as well for HCN over here. I'll come back to that one later, a bit less significant, but tentative, let's say. So I think a lot of the comet scientists in the room might say, oh, well, okay, look at the points there. The points for the big comets are actually clearer. So those are comets. The big comets are the ones that were observed far from the sun. And you're going to have water sublimation becoming less efficient when you come far from the sun. And also, obviously, your CO2 H2O ratio will increase. So we looked into that, whether the trend was real or whether it was just an effect of the heliocentric distance at which we observed the comets. And so that's some of the tests we did. Well, that's plotting simply at the top, the this abundance ratio versus heliocentric distance. And indeed, yes, you have a trend. That's something we know about, no big surprise there. So what we did to see how this trend was impacting our results, we did two things. First, we fitted the trend over here, and then we subtracted it from the data. And the second test we did is we looked at only the data between 1 and 2 AU. So to really get rid of this regime where water sublimation becomes less efficient. And in both cases, we got the same results. The trend for the CO holds, very significant still. The trend for HCN disappears, or at least is not significant anymore. So it seems that for CO, we do have a trend of increasing CO abundance for larger comets, which is very interesting and was predicted by the model. What that means, whether other mechanism can lead to the similar trends or whether that validates the model is another debate, but the trend is there. So yeah, coming to the conclusion, doing a big meta-study from literature data, we found a trend between the relative carbon monoxide to water abundance ratio in comets and their sizes. I didn't mention it, but the trend is significant for both ecliptic and nearly isotropic comets. We checked, and that change is not that trend is not dominated, and not or at least only produced by the difference in heliocentric distance at which some of the comets have been observed. And we see some tentative weaker correlations for other species, but we can't confirm anything with the amount of data because for a lot of them, we just don't have the data to confirm it. So that's where I'm going to mention the JWST, because that's the perfect tool to actually fill these plots. And what we need is not only a lot more comets for which we have size measurement and also CO, CO2, H2O measurements, but also all the volatiles, because the trend should hold for other volatile species like methane, for example. And so we really have the opportunity to check that trend on a larger number of species and whether it holds on a larger number of comets. I was very interested by Sarah when Sarah mentioned that there might be a tentative detection of water in 29P, because I would really like to see it on the plot when it comes out and see what happens. And the last thing I want to mention is that all the data tables that Jamie has painfully collected, all the data point, scanning paper, entering everything into nice tables, they are available online. So if you want to try to reproduce the results, I invite you to go and look at the paper. There's all the information there on how to access the data tables online, and feel free to play with them and try to see what you can find with them, or use them for other purposes if the data are there. Please go for it. So thank you very much.
Hi, thank you. Yeah, I just wanted to say I think it's great that you're sharing the data with the community. So thank you for that. And then my question is regarding your method of fitting your trends, and how do you decide whether a trend is significant or not?
So we did Pearson correlation coefficients, and so I can't remember the value we've set. So we've got basically 1 sigma, 2 sigma, 3 sigma threshold in the significance, in the p-value basically of the correlation. And so when I'm talking about CO being significance, it's more than 3 sigma significance. In there, all the values for the coefficient, the correlation coefficient and p-values are in the paper, but I just didn't want to put just a bunch of tables on the slides. But yeah, all the values are in the paper.
Nice work. So I have 2 quick questions. First is in your plot, and then I suppose you could include both short period comets and long period comets. So I was wondering how many there's dominated by JFCs or half-half.
I don't have the numbers in mind, sorry. Okay. We have both of them, but I think, yes, we have a larger number of JFCs just because we have more that have known sizes, unfortunately. Right. So the limiting factor is really the size. So I'd encourage everyone with JWST observations to look at gas composition, to try to have a go at getting a size of the nucleus as well, because as things, it seems that there's interesting way to test formation models of comets by looking at these.
The second question is your CO to water ratio has artificial limit beyond 5 AU that water hardly sublimit is water ice. So you have an artificial cutoff.
Yes.
Around 5 AU. Beyond that, it's just CO or CO2.
Yeah, I think we have only 1 point at 6 AU. Yeah, but yeah, you're totally right. And that's like really a kind of a outlier, this very distant point. That's why we did the cutoff between 1 and 2 AU, just to like get around that.
Okay, thank you.
I got one for me. Oh, good job. So yeah, I want just to check with you. So did you try also to look at the trend of the daughter species? So, and with the distance, I know that we cannot get them above 3 AU, but at least you will get some point over there in your plots.
Yeah.
For example, like, you know, we have been working on that on TRAPPIST, but we were like, I think to get that sample also in this study.
Yes, no, good point. And thank you for the question, because I forgot to mention it when I was talking. We did all the same analysis for the daughter species as well, and we didn't find any trend. But we did C2, CN, NH, NH, and I'm forgetting something. But yeah, we did NH2, sorry. We did the daughter species as well. It's all in the paper, but we didn't find anything significant there.
Thank you.
Next up, we have Andrew Rifkin from the Applied Physics Laboratory. I love your talk, yet. Me neither. But I know it concerns the James Webb observations of several asteroids.
Hey, don't start my time yet.
There you go. It's all yours.
All right, thanks. It's a pleasure to be here. It's great to be in Cape Town. Thanks to all the organizers and all the speakers for, oh, there it is, for a great session. So I'm going to be talking about Ceres, Pallas, and Hygeia. Here's some of the usual suspects on the list there. I also am going to shout out, of course, to Heidi Hamel, who got the time. This is part of the Heidi Hamel guaranteed time observations. So if you know one thing, or if you were to spot one thing about asteroids right away, it's that a lot of them have high albedos and a bunch of them have low albedos. That is kind of a fundamental fact about them. And here, this graphic put together by Emily Lakdawala shows many of the asteroids that have been visited by spacecraft. The brighter, higher albedo asteroids are associated with rocky compositions or metallic compositions, and are generally water or OH poor. Vesta and Didymos and Dimorphos are also among that group. The darker surfaces, and there are comments on here as well, are associated with ice or organics, and Bennu and Ryugu and Ceres also fit into that group. And low albedo asteroids are of particular interest because it's not just their albedos that seem to show them as different, but they seem to be different at really fundamental levels. There's a geochemical evidence and an emerging paradigm that, of course, is being tweaked as these things are, that there were two completely separated reservoirs of solar system material early in solar system history. One is associated with the carbonaceous chondrites, the CC group, and the other, the NC group, is associated with basically everything other than the carbonaceous chondrites. And this is thought to be a consequence of how things develop, that Jupiter probably kept these two reservoirs apart from one another, and planetesimals formed with just one of those compositions. There are various snow lines, particularly in the outer solar system, so that the outer solar system group could potentially have different things accreted to them. And then, of course, there's the planets move around, planetary migration, things mix, hijinks ensue. And inventories of what's out there should have gone. Let's try one more. There we go. And so this is basically what I just said there. So inventories of the asteroids show that, again, there are basically a high albedo group and a low albedo group, and the low albedo group is really, really numerous. They are more difficult to discover for a particular brightness level, brightness limited surveys, at least in the visible, but they are dominant in the outer part of the asteroid belt, and almost as equal in number as higher albedo objects, even in the low albedo, even in the inner asteroid belt. So looking at the three largest low albedo asteroids, we have Ceres, Pallas, and Hygeia. Ceres is up there. It's the one that's marked Ceres for the folks online. And it's almost 1,000 kilometers across. It was visited by the Dawn spacecraft. That is an image from the Dawn spacecraft. It is extensively aqueously altered. There is evidence of ammoniated material in its phyllosilicates, which has been interpreted as an input from the outer solar system. Maybe it formed in the outer solar system where ammonia ice was available, and then it was transported inward. There was cryovolcanism. Maybe there continues to be cryovolcanism, these bright spots, and you can kind of see a bright patch on Ceres there. And tying in a little bit with what Geronimo mentioned, it's thought to be a relict ocean world where it perhaps experienced some of the similar kinds of processes that bodies like Europa or Enceladus or Ganymede also did, but because it's not orbiting a planet, it didn't have continued input of tidal energy. It kind of died out. Pallas, up there on the upper right, is about half the size of Ceres. There's evidence for aqueous alteration, but no ammoniated minerals. And unlike Ceres, it's a parent body for a collisional family. So there are a lot of objects that are smaller that are in similar orbits to Pallas. We think Pallas had a collision, and these are pieces of Pallas. and it thus may be the parent body of some NEOs. It's associated with the asteroid Phaethon, at least in some models, and so is also then ultimately the parent body of the Geminid meteorites. And then Hygeia down there below Ceres is about, again, a little under half the size of Ceres, and so about a tenth the mass. And it seems to be a spectral twin of Ceres in all of the wavelengths we have, so we might imagine it has a similar history or similar series, processes a series. It also has a collisional family, but we don't think we have any NEOs or meteorites, at least that we've identified from Hygeia. So when we look at low albedo asteroids, or at least I, like to look in the 3-micron spectral region, because that's the region where we have absorptions due to things like OH or CH or NH. And so we can measure these kinds of minerals, these hydrated or ammoniated minerals. The specifics of where the band centers are, for instance, in this plot, show that can give you the specific compositions. The trick is, and I'm going to have to skip ahead too, I think, is, whoops, that's too bad. I didn't make the plot that I should have. Is that the wavelength where that band center falls is obscured by water in the Earth's atmosphere. And so that makes it difficult to tell what's going on. However, we can still make some measurements from the ground, and we've come a long way. So for instance, this plot here shows both what's blocked by the Earth's atmosphere and what we can see around it. And both Ceres and Pallas are on this plot. Pallas is the top trace. Ceres is the second from the bottom. And again, Ceres showing these absorptions that we think are due to ammoniated minerals, while Pallas just shows something that we think is due to magnesium or iron in phyllosilicates. The meteorites look a lot like Pallas and the one under it, and we don't see anything that looks like Ceres. So the reason we want to look at these are big, bright objects. They're, Ceres can get to 7th magnitude. We're using this powerful telescope. What are we doing? Why aren't we looking at AGNs with signal noise of 3 or whatever the other people in this meeting are doing? It's a tough crowd. No one. So these basically are planetary embryos, and they're planetary embryos next door, right? So we're really not going to be seeing planetary embryos in other systems, at least up close. Missions like Dawn are complicated. They can be expensive. Some targets are much harder to visit than others. Pallas has a very high inclination, and so getting a rendezvous mission up there is going to be very difficult. And again, ground-based observatories really can't match the quality of JWST, and they miss these important wavelengths. So this plot here on the right shows a spectrum of Bennu, and that box shows kind of that band minimum that tells us specifically what kind of phyllosilicates we're looking at, and we can't get it from the Earth, but we can get it from JWST. So this, I don't expect anyone to really look at this. This just shows the data that we took with NIRSpec for Ceres, Pallas, and Hygeia. We took 2 different filters. As with all of these other things we were talking about in this session, we have 3 or 4 or 5 minutes worth of exposure per grading setting, so it really went by very quickly. I suppose all of these, my talk is going to be longer than the amount of time it took to take all of this data. And here is what they look like. So as I said at the start, the time was obtained via Heidi Hammel's guaranteed time program. We have both NIRSpec and MIRI measurements. I'm not talking about the MIRI ones today. The MIRI observations are still under analysis. We knew that they would be difficult to analyze for, again, reasons that Geronimo talked about with Mars. Everything is saturated. We knew they were going to be saturated. And at least in the case of MIRI, part of the plan was to figure out how to analyze saturated data in hopes that we could then do something that could be of general use. Some of the NIRSpec wavelengths are also saturated. Again, we kind of expected that. So the top there is Hygeia. The second one is Ceres. And again, even in this wavelength region from 2.6 to 2.8 microns or so that we can't get from the ground, they are still spectral twins. That absorption kind of near 3.05 microns is due to NH4 in minerals. And that is independent of, so it's due to NH4. The one at 2.7 microns or so is due to OH. These are different causes, and so we can treat them as independent things when we analyze them. First thing to do is compare them to meteorites. This shows Pallas compared to a few different C-type meteorites or carbonaceous chondrite meteorites. That vertical line shows where the band center for Pallas is. And that band position shows a very magnesium-rich phyllosilicate mineral. There's really no evidence of iron in this phyllosilicate. There's also this very sharp feature that you can see in Pallas that's at the same wavelength as this broader feature that seems to be consistent with something like talc. These meteorites that I'm showing along with this are from a variety of different carbonaceous chondrite groups, so we can't necessarily say that it looks like a C2, CM, 2 or anything like that. And since Pallas is a 500-kilometer planetary embryo and has undergone extensive processing, that might not be the most apt thing to do either. Comparing to other asteroids, here we have Pallas versus Ryugu and Bennu, both from the spacecraft and from their samples. The band centers are pretty similar to all of these. And we can look at this and infer that Pallas and Ceres and Hygeia probably didn't have a lot of space weathering, or at least their space weathering is not affecting their spectra, because space weathering moves absorption bands to longer wavelengths, and these are already pretty short. So it's hard to get them shorter than this. That's a terrible figure, and that's my fault, but it's a very old scan. So basically, we can take this one step further and try to quantify how much water is in these spectra, how much hydrogen do we get from these spectra. And I'll just skip ahead a couple. Basically, there are strictly empirical ways where you take your carbonaceous chondrite in the lab and you just say, here's the band depth, here's the amount of water, go. There are somewhat more analytical ways involving normalized optical path length. And this kind of shows what we have for Ceres, Pallas, and Hygeia for applying those same spectral techniques to Ryugu and Bennu, averages, and then for Ryugu and Bennu, the lab sample measurement. And it maybe looks like a bit of a mess, but things are holding together reasonably well. And Ceres and Pallas have CM-like water amounts or hydrogen amounts. Hygeia is a little bit less. The thing of maybe some note and perhaps concern is that Ryugu and Bennu have a big spread. So we clearly have a lot more work to do in understanding how these techniques actually work compared to the samples in hand. I see you standing there. So just to quickly hit one more point, we have some other wavelength regions where there are some features that we are still trying to interpret. Slightly short of 2.7 microns, there are absorptions that we think are OH combination bands. We think they're real for various reasons. And then Hygeia shows an absorption. There's a gap due to a detector gap. That's just a physical gap. So we're not sure if that's one absorption or multiple ones. We're still also trying to figure that out. So I will just note that on this slide that JWST really was necessary. The increased spectral resolution let us see that extra sharp absorption on Pallas. And then this is also going to help us hopefully try to do a better job of quantifying getting water from spectra so that we don't have to go to JWST for 100 asteroid spectra. We can just do that part from the ground. So conclusions, I'll let you read those there and give you 90 seconds to ask me questions if you like, I guess.
Hi there, Nick from SAO. Maybe this is a question for all JWST planetary science users with the saturation issue. Or maybe it's a stupid question, but can't you guys just request to defocus the telescope, or is that just frowned upon?
I do not think that is an option. I think that certainly they've worked very, very hard to get the PSF stable and to kind of publish that. I don't think they would be into changing that. Yeah, that's true. That's true.
Point of kind of things.
Yeah, it takes 5 minutes with exposure. These things rotate. Would you expect to see any difference if you did a different 5 minutes in the spectrum?
No, not on these three. I mean, Ceres is famously homogeneous spectrally. You know, the white spots, the bright spots and stuff are really don't show up in the global spectra. But you know, if they want to give us, you know, 6-8 hours per object to give it a shot, we'll take the time.
Then we have the last speaker of today's session, Miriam Ganoun. I hope that was approximately correct, from Ucumiden Observatory, and she is going to talk about new parent bodies in meteor streams. Yeah, that's for your slide. The online people can't see if we point, so describe it.
Okay, thank you. All right, so hello everyone. My name is Miriam and I'm an associate researcher at Ucumiden Observatory of Marco. And I'm so happy to be here in Cape Town and to share my work about discovering new parent bodies of meteor showers as I'm suggesting a new methodological approach. So yeah, so the main phenomenon of the star of my work are meteors, often called shooting stars. So basically, what I'm doing is optical observations of meteors, analysis, orbit computations, to be able to find parent bodies of meteor showers, either asteroids or comets, and even calculates the location of the possible location of meteorites fall. And just a small review. One of the possibilities is that it all starts with an asteroid giving birth to what we call a meteoroid in the solar system. If it enters the sky, the Earth atmosphere, it becomes a meteor. And if it survives the atmospheric fall, it becomes what we call a meteorite. So basically, they are all the same body with different names and properties when placed in different placement in our solar system. And when we say the same body, we're basically talking about originally the same orbit if we neglect all deviations and all. So that's why the main object, the main goal of my work is actually to detect meteors on the sky, and by comparing orbits, either find the parent body, the asteroid or the comet, or calculates the meteorite fall, the location of the meteorite fall. What meteors can also, as you know, originate from comets. Once a year, so the Earth orbits the sun for 1 year, and for the same period of each year, the Earth will go through the comet tail full of, let's say, dust and tiny particles that enters the atmosphere at the same time, which results in the meteor shower phenomenon. So basically, when a large number of meteors enter the sky at the same time around, they appear to enter from the one single point, which is called the radiant. So again, my work is to observe meteors and try to find the parent body, asteroid or comet, and calculate the placement of meteorite fall. But the problematic I've been focusing on is that several meteor showers are identified and added to the IAU list of meteor showers every year, and using a one threshold single linking criterion called DSH that was first introduced by Southwell and Hawkins in 1963, and it is actually, it's a small value of DSH indicates a high similarity between orbits. So, and only 6 similar orbits are enough to identify a new meteor shower or identify an association, all right? So a value of 0.25 is often used. However, the calculation of DSH, of this criterion, is based on the calculation of the semi-major axis and eccentricity of orbits, which have been proven in many late works to be very poorly indicated, I mean, in terms of precision. So I thought of suggesting a new method, and rather than calculating the DSH criterion, maybe compare the apparent radiant location and geocentric velocity, and compare an angular distance between radiants of meteor showers and known parent bodies, asteroids or comets. I've been focusing on asteroids. And then, in order to fully explore the influence of velocity, I considered a variable velocity threshold based on the percentage of the measured meteor velocity. And instead of 6 similar orbits, an association is identified when at least a total number of 50 similar orbits is found. But actually, we've tested a lot of threshold values, and we ended up considering these as they give more reliable results. And after all of this, I've been lucky to collaborate with Pavel Cotton and Čapek from Czech Republic Institute of Astrophysics to perform a statistical test, and we calculated what we called PCO for probability of chance occurrence, which can be actually very high due to the very large number of orbits computed, since we have, thank God, a large number of meteor networks in the world. So I've obviously used the Moroccan Meteor Network database, but I wanted to actually explore this method using databases with much larger, like a huge number of data. So I work with Edmond database and Sonotako database. So it has like, this is an example of the number of computed orbits from 2007 to 2020. So it has a huge number of orbits. So we use that to test if the association between orbits, either between an orbit and a parent body or between the mean orbit of a meteor shower with an asteroid, is just a coincidence due to this large number of orbits. Okay. All right. So, yeah. So, as we were expecting, we had much less association between asteroids and comets and meteor showers, but at least they were identified using much more precise criteria, if I might say, and when at least 50 orbits were similar. So 26 new potential parent bodies were discovered using this method, but after performing the statistical test, as you can see here, the values of the probability of chance occurrence were pretty high for the majority of these new parent bodies, new asteroids, except for the first 4 asteroids, as you can see. But we ended up not considering the fourth one, since 50 and 60 are still very high probability of chance occurrence. And also for the second one, it has a 97% of chance occurrence for the Sonotako database, although the other one was not high. We ended up canceling this. So as a result of all of this, we obviously confirmed some known parent bodies of meteor showers, but we also discovered new asteroid parent bodies of meteor showers that were never linked to meteor showers before, and there are even linked to hundreds of meteors from both Sonotako and Edmond database. So yeah, our method led to much less confirmed association, but at least they were identified using a much reliable test. And this method actually, or this work, highlights the difficulty of computing an accurate meteor orbit from optical observations of meteors, which highlights the need for robust statistical tests. And I'm probably gonna be working on this for next. Actually, it is very legitimate to question the veracity of the existing meteor showers that are added to the IAU list every year. So in Morocco, I want to talk about our Moroccan Meteor Network. It started in 2012. with only 2 directional cameras. But nowadays we are collaborating with the Global Fireball Observatory of Austria. We're collaborating with the Global Meteor Network. We even created a new meteor network in Morocco called MOFID, which stands for Moroccan Observatory for Fireball Detection. So we are equipped with all sky cameras and stuff. So, and with the goal of being able to install more than 100 cameras in the Moroccan territory. And again, the goal of this Moroccan meteor network for now is to detect meteors in order to find parent bodies and make it easier or facilitate the search for meteorites, especially knowing that Morocco is the 2nd country in the world to recover meteorites. And one example of a successful results we had is that this actually a fireball, a big meteor that was observed from Ifrane in Morocco in different stations. Actually using my program, I could actually find the parent body. This is the 2016 PQ asteroid. And our collaborators from Ain Shok University of Casablanca already found the resultant piece of the meteorites, which actually sum up the goal of our network. So I'll be happy to answer any questions. If you are, I mean, if you want more info, contact me, or even suggestion. Thank you for your attention. Thank you.
Okay, could you estimate the size of the parent body of the last fireball event?
Sorry, the size of?
Yes, estimated size of the parent body, I mean the meteoroid.
The meteoroid, it's actually pretty small. I mean, relatively pretty small. I think it's 2 kilograms, but the size I don't remember. Do you remember the size of the meteorite they found?
No,
I remember the weight.
I'm not asking not meteorite. I'm asking meteoroid.
Oh, meteoroids in the solar system. It's actually it differs actually when 2 asteroids collide with each other. It's like 2 rocks colliding with each other. So they give like small millimeters to relatively big meteoroid. That's why we can obtain small meteors in the sky or fireballs, like when they are much bigger. Okay. Did I answer the question? If I understand. Thank you.
Thank you for a nice talk. Are you
Thank
using the Japanese amateurs data Sonotaku?
Sonotaku, yeah.
Yeah, thank you for using our data.
Thank you.
Anyway, it's rather the brighter meteors, so
yeah,
not doesn't include the
yeah,
fainter
totally.
one. So do you expect the further study if you use the fainter one?
Yeah.
Can you apply your method to identify the?
Yeah, totally. We can apply that. I mean, we need maybe a different equipment to be able to observe them. But for now, we're working on the bright meteors. If we are lucky enough to have them. Luckily, we have the databases, Sonotaku and Edmund. But of course, I'm actually considering that, even interested in that. Thank you. Hello.
Hi, Andy Rifkin, Applied Physics Lab. Great talk, interesting topic.
Thank you.
Do you have any, do you know the spectral types of the asteroids that you're finding the showers for, or do you intend to figure that out?
Actually, very lately, I've been working on a topic, but I don't do spectroscopy. So I just developed a program that actually gives the synthetic or theoretical spectrum of meteorites, which we know the chemical composition. And my goal at the beginning was to actually compare those spectrum with either spectrum of asteroids or if we can actually observe the spectrum of meteors and find association. But it's actually a new thing. I'm still figuring that out. I actually have the I did the classification. I have the synthetic spectrum of meteorites, but never been able to do the rest.
Yeah, it would be an interesting comparison for,
Yeah.
I forget which one, right? For instance, if someone got the spectrum of 2016,
Yeah, so
whatever
that.
it was. And
Yeah, totally. Thank you.
We got also a question from online from Zoom from William Waller. I think is related to spectroscopy question. Is spectroscopy of the brighter meteor possible? And if so, can it help constrain the chemistry of the meteorite? So it's a
Yeah, already answered.
Andrew.
Yeah, exactly. Thank you. Thank you so much.
Thank all our speakers again, and also thank you.